Okay.
Okay.
Everything is fine?
Yes.
Can you start?
Yes. Just a little bit of water and we can go.
Okay. So we have to start this PhD defense. We are here together, and I am very, very glad about the presence of everyone. I would like to say thank you for Professor Carla. It's very, very really, it's a pleasure to have you over here with us. And I would like to say thank you for Professor Alain, again with us, with our research group. It's very kind about you to have to spend this time with us. And I would like to say thank you, also thank you for Sergio. Sergio, I know Sergio for many times, a very long time ago, since I was in my master. And I would like to say thank you as well for Professor Thiago. Professor Thiago is brand new in our department. He is our last, how can I say, last, not acquisition, but I think I have to say acquisition. And finally, I would like to say thank you so much for Sixto to have this partnership with us. And it's a very, very pleasure to have this excellent research with us and to have the opportunity to give the opportunity to share his expertise with us and his research and everything that Sixto did for Elise and for me. I would like to say thank you. And then I would like to say about the rules. We have 40 minutes for Elizângela to have her presentation. And after we can start the discussions and the questions. In Brazil, we use it to start with the external members, of the Jude, and then I think that because ladies first, so and because Carla is more in the south of the country, we will start with Carla, if it's okay for everyone, of course, and then I would like to have Alain and the second time, and after Sergio, because Sergio is very, very close in the distance, in the relationship, of course, with our PhD program. And then finally, Professor Thiago, because he's an internal member of our research program. And after that, the co-supervisor and supervisor could have some small time to say something. And we can, after all of the questions and discussions, we have to ask for Elizângela leave this room, and we can decide if Elizângela could be a doctor or not.
Camila, can I just ask something because of the the technical part here? I will just leave. In reality, I'm gonna leave the room and let the Zoom meeting room here for you. Or if it's okay. I will stop the YouTube, okay, and then okay.
I will connect again with this link from the host. Do you know the password? I have to connect again with Tassiana's password, and then I can stay here.
You can say okay, but then okay, it's just because of the YouTube. In the
okay, we will end. We don't need that.
Okay.
So I just wanted to say that between the discussions when one judge is discussion or is doing the questions for Elizângela, I think that everyone could be free to just ask you the same things or to like to contribute with the same discussion. Okay, I think that it's very flexible. We don't have to be like strict with this kind. We are here to collaborate and to share our knowledge, and it's good for everyone. So thank you again for everyone, and good luck, Elizângela. And now it's your turn.
Okay.
I will just turn off my camera and my microphone just to allow clarity, and then we can open again after the presentation.
Okay, thank you all. So now I'm going to share my presentation.
So we start the record, okay? You have to give me permission, or we can start the record as well.
The record, okay. So I'm gonna start. You can start now.
Start.
Okay.
Yeah, the record.
The record. Ah, okay.
Yeah.
The record.
Good, because after we can leave that in our research group. If
recording is in progress now. So, good morning, everyone. Buenos dias, bom dia a todos. My name is Elizângela, and I'm a PhD candidate from the Federal University of Minas Gerais. And today I'm going to present the thesis entitled Removal of Contaminants of Emerging Concern and Disinfection in Secondary Municipal Wastewater by Circumneutral Solar Photo-Fenton in Open Reactors. My supervisor is Professor Dr. Camila Amorim, and my co-supervisor is Professor Dr. Sixto Malato. So, what are these contaminants of emerging concern, the CC, that are the main focus of this thesis? They are several groups of organic compounds and contaminants that can be found that are used daily in our human lives, and they can be found at very low concentrations in the environment. And to detect such low concentrations, we need advanced techniques for identifying these compounds. In this way, they have been investigated over the last few decades, and even we have found some evidence of impact on the human health and ecotoxicological effects for these contaminants, even at such low concentrations. But still, there are more studies for a complete evaluation for more compounds, and also there are many substances with unknown effects. And the combination of effects of more than one substance. In this way, there is an increasing concern about the impacts in the environment of the substance. And regarding the legislation for environmental matters, we have seen that around the world there are more legislation focusing on water matters and both drinking water and also surface water, but there is still few legislation regarding the effluents from municipal wastewater treatment plants, which are a main source of these substances and trends in the environment. And Switzerland is a country with a legislation that focuses on the removal of a group of selected indicator substances, and they aim at an efficiency of 80% removal of these substances in the effluent of municipal wastewater treatment plants. In this way, considering our scenario of treatment plants in Brazil for wastewater, we see that we still have a low coverage for both collection and treatment of wastewater, a low collection in terms of number of population, and we need to improve this treatment because most are also up to the secondary stage. Regarding the technologies, there are many small treatment plants units, and they use process such biological process such as anaerobic reactors and also stabilization ponds. Regarding the size and the maintenance conditions of these units, many of them are of very small size, and in the country stations, the treatment plants with a larger size are usually of conventional activated sludge and a aerobic process. And due to the large amount of stations with a small flow, small size, and they have also presented some operational and maintenance problems, which most of them need update nowadays. In this way, if we cannot remove the contaminants of emerging concern with such conventional biological process, once these processes are focused on the removal of main organic matter, nutrients, and other contaminants, we need to apply advanced treatment. For example, separation by membrane technologies, adsorption on activated carbon, and degradation by ozonation. And these are examples of very established advanced treatment technologies nowadays, with ozonation and advanced and adsorption by activated carbon as some processes used in countries such as Switzerland. And ozonation is an example of an advanced oxidation process, which are a group of advanced treatments which they focus on the generation of reactive oxygen species, such as the hydroxyl radical, and ozonation is one of them. Another very well-known process is the Fenton's reagent, and its irradiated version is the photo-Fenton reaction, and they have been used and proven to be very efficient for industrial and municipal wastewater, including disinfection. And the Fenton reagent is based on the generation of hydroxyl radicals by the oxidation of hydrogen peroxide in the presence of a catalyst, the ferrous iron. And this catalyst can be renewed in the reaction in the medium by a photocatalytic cycle irradiated from solar, a natural light, or also artificial irradiation such as UV light. And these radicals will decompose compounds, organic compounds, in a non-selective way, and we can have byproducts such as a completed mineralization with CO2, water, and anions. But we can also achieve, in most of the cases, we can achieve an incomplete mineralization, partial mineralization. And we have to investigate if these compounds can be toxic or not. In this way, we usually we can proceed with the reaction until the complete mineralization, but sometimes this is not necessary, and we can try to focus on other goals. Such, for example, in Switzerland, they have established a removal of 80% for the CCs sum of selected CCs, or we can also think of proceeding with the reaction until there is no detected undesirable effects, for example, toxicity and estrogenicity. Regarding the photo-Fenton reaction, this reaction takes place usually in the Fenton reaction takes place usually in an acidic pH around 3 for the solubilization of iron species. But to promote a more efficient reaction in a condition in which the effluent can be further reused or discharged in the environment, we try. It has been investigated over the years, and an application of chelating species such EDDS, EDTA, to promote the solubilization of iron in a neutral pH. In this way, this work focused on EDDS. There is a more environmental friendly complexing or chelating agent in comparison to EDTA. Or the strategy known as the sequential addition of iron also. In this way, to apply the photo-Fenton reaction using a sustainable renewable light as the sun, we can use some solar photoreactors. And among these, there are two types of reactors that we can say: the compound parabolic collectors, which are a concentrating type of design of reactor. And also we have an example of an open reactor, which is the raceway pond reactor. The CPC reactors are very well known, applied for highly concentrated toxic effluents with a higher concentration of contaminants. While the raceway on the RPR, it has been proposed to promote the treatment of non-toxic effluent with a lower concentration of target contaminants. And the idea of using such reactors is that they have a simple structure. They can be scaled up for larger treatment, so we can achieve higher treatment capacity in comparison to CPC. And for the promotion of the disinfection and treatment of municipal wastewater, we aim at short treatment time due to the large flow of effluent. We need to use a low iron to achieve a low iron residual concentration, and for this to work at low iron concentration, we need to use a higher liquid depth in the reactor to promote a large optical pathway for the reaction. In this way, we can see the advantage of an ampere reactor as a lower cost and less energetic demand kind of reactor. In this way, this work justifies for a high potential of the application of the photo-Fenton reaction for the treatment, for the tertiary advanced treatment of municipal wastewater treatment plant effluent. We can see a solar energy as an alternative and sustainable light source that is widely available in Brazil. Also, we need to think about the actual scenario of municipal wastewater treatment plants in Brazil, in which we need to improve the efficiency of currently stations, and also we need to invest in low-cost technologies to achieve such improvement. And we cannot forget to think of a future scenario in which Brazil will follow the international trend to think about the removal of or the control of the CC's contaminants. In this way, we have proposed three main questions as literature gaps, which will guide this work in three main chapters. And the first one is actually two questions with, are there any studies showing simultaneous information on disinfection and CC's removal for this treatment plant effluent? Also, which secondary biological processes are applied in the municipal treatment plants in these studies? The second question, we focus on a possibility of using an aluminum reflective surface to improve such circumneutral photo-Fenton reactions using low iron concentrations in open solar photoreactors. And finally, we ask ourselves if the circumneutral photo-Fenton reactions can be as efficient for CC removal and disinfection in other types of effluents from different biological processes, such as anaerobic. In this way, the goal of this work is to investigate the applicability of the circumneutral solar photo-Fenton reactions using an open photoreactor for the treatment of municipal secondary effluents, both from an aerobic and anaerobic biological process, considering disinfection and removal of target CCs, which are acetaminophen, caffeine, trimethoprim, sulfamethoxazole, carbamazepine, and diclofenac. In this way, we in the first chapter we have focused on a literature investigation, which we present here just a brief summary of the results, and we have published a paper, a literature review with the results from this chapter. The goal of this chapter was to perform a systemic review of the literature regarding the treatment for the simultaneous removal of both CCs and pathogens through disinfection in domestic, focusing on municipal or domestic wastewater. And with this methodology, we could identify highlights, obstacles, problematics, and opportunities to work within the solar photo-Fenton based treatment in open reactors, considering all opportunities and matrices, opportunities, everything from this literature review. We used a methodology known as PRO-C, knowledge constructivist type literature review methodology. We used papers published between 2008 and 2018, and this literature review is structured in three main steps. which are the construction of a selected portfolio with specific keywords in many databases to gather a selective and group of articles that can answer our questions. Then we perform a bibliometric analysis of the literature, considering the number of citations, the relevance of these papers, and finally, with the final selected papers, we go in a deep review analysis of these papers and focus on their strengths and weaknesses to elaborate our questions, guiding questions for to answer our initial questions. In this way, from this portfolio investigation, we could see in the final refined portfolio a predomination of words such as oxidation, chemicals, AOPs, and membranes, which indicate that we are we can follow this trend of analysis of chemical and oxidation treatment for the removal of CCs. This has been investigated in the past few years. Also, in the refined search, we could detect that they mention more about the groups of contaminants, so more than one contaminant is investigated. And these groups are the pharmaceutical drugs, personal care products, including the pharmaceutical drugs, antibiotics, and endocrine disruptors. While in the non-refined search, a specific contaminant could be identified. Finally, we could answer our guiding or initial questions, and few papers focus on presenting results of both removal of CCs and pathogens or in disinfection, and most of these were more recently published papers. And finally, we could see that among all investigated treatments, ozonation, it was the one with most development, and it has even applied at large scale, for example, in Switzerland. Finally, we took a deep literature look in the past few years of the published literature with photo-Fenton reactions in the wastewater reactors, and we could check how most of works are published with conventional activated sludge effluents from both simulated and real effluents, actual effluents. We could see the range of concentrations fortified in the effluent, how low iron and hydrogen peroxide concentrations have been used, also the range of liquid depth used in this treatment, and among other parameters. Finally, we could see the potential to apply this for municipal wastewater treatment without regrowth of bacteria after some time, and the possibility to not increase toxicity after the treatment. In sequence, we performed a second part in the chapter 2, a laboratory work with the evaluation of the use of the aluminum reflective surface in the open reactor for the removal of CCs in a secondary effluent from unactivated sludge municipal wastewater treatment plant. From this chapter, we published 2 papers with results in natural water and real wastewater. And the goal of the chapter was to investigate the use of this aluminum surface in the bottom of the open reactor to remove contaminants in different conditions and at both bench scale and then semi-pallet scale. In this way, we selected 6 relevant pharmaceuticals and also caffeine that is used in many products, not only in the pharmaceuticals products. We select acetaminophen, diclofenac, sulfamethoxazole, trimethoprim, and carbamazepine due to their different properties that made them also easily monitored in a single chromatography injection. For the treatment, for the metric collection, we used both natural water and this aerobic effluent from the conventional activated sludge system in the city of Almeria in Spain. The effluent was properly stored and characterized and used after two pre-treatments, which were the pre-filtration to reduce turbidity and suspended solids for the photocatalytic reaction treatment. And also we had to reduce the total inorganic carbon with a partial carbonate neutralization due to the elevated content of inorganic carbon in this effluent even after filtration. We can see that these effluents, and both the effluent and the natural water are characterized with a high elevated conductivity and presence of inorganic species. Also, we can see some presence of turbidity even after the low organic carbon concentration in this effluent, treated effluent. So for the sample preparation and identification of compounds, we used an HPLC, the liquid chromatography, with a diode array detector from Agilent, and we performed the determination for, at the same time, for the 6 compounds, constructed calibration curves for each one of them, and we used a direct, just after a sample filtration, we directly injected the samples in the HPLC for experiment at 100 micrograms per liter concentration. When we reduced the initial concentration, we had to apply a solid phase extraction with Oasis HLB cartridge to concentrate the sample. And finally, in the real effluent, without fortification, we detected the presence of the concentration of contaminants in the effluent with liquid chromatography coupled to with mass spectrometry detection by a Q-trap equipment. During this analysis, over about 150 compounds were investigated, in which we found 60 compounds in the effluent of analysis, with a total about of 25 micrograms per liter of concentration of these compounds. Reactions in laboratory scale were performed with and without the aluminum reflex surface in a solar chamber, a solar simulator from Atlas. We performed experiments with an irradiation level about 30 watts per square meter, a normal sunny day at noon. We performed experiments with different liquid depths, different low iron concentrations, a fixed hydrogen peroxide concentration, with different concentrations of initial concentration of contaminants in both methods. In a semi-pilot scale, we performed also experiments with and without the aluminum surface. We monitored both concentrations of contaminants in natural water, but in real wastewater, we detected with a mass spectrometry the concentration of species in the effluent. We tried this time just 2 concentrations of iron at the best liquid depth. In this way, results from this chapter, we could see in natural water at lab scale with the highest initial concentration of contaminants, a pattern or a degradation pattern for each of the contaminants that this we will follow throughout all the work in every reaction. Caffeine being the most resistant one in red for treatment, while diclofenac in green is the easiest one to degrade due to its susceptibility to photolysis. And this can be seen in all of our results. Regarding the composition of the complex iron 3 DDS during reaction, we could see that after the complex was decomposed, we would see the decreasing in dissolved iron concentration, which would reflect in a slowing down of the hydrogen peroxide concentration. And this is expected for the decomposition of the complex degeneration of ferrous iron, which leads to the generation of a hydroxyl radical that attacks the contaminants. So when this the consumption of hydrogen peroxide, the dissolved iron concentration decreased, we see a slowing down in the reaction, the treatment. and this could also be seen throughout experiments. Regarding the control experiments with photolysis, photoperoxidation, and a dark photon light without the light, almost no decomposition of compounds except for photolysis and photoperoxidation regarding the diclofenac in green lines, with a higher degradation of diclofenac through photoperoxidation. Regarding the analysis of different liquid depths, we could see that we could achieve a higher treatment in both liquid depths in a short treatment time. And in this way, we focus on the highest liquid depth to promote the highest treatment capacity in further analysis. And regarding low iron concentrations, we could see that the lowest iron concentration could, with the aluminum surface, could show some improvement in the reaction. However, they did not perform as well as a 3 milligrams per liter or 0.045 millimolar of iron concentration. In this way, we performed in the following sections experiments with the 3 milligram and 5.5 milligram per liter of iron. So in the semi-pilot scale, in the RPR reactor with natural water, we could see for both initial fortified concentration of contaminants, an increase, a similar reaction short treatment time, and this treatment time and efficient were closer to the results in lab scale using a lower concentration, initial concentration of contaminants. This means we could achieve a closer result to possibly real conditions in natural matters in the environment. And during natural treatment in natural water, it was required just short treatment time and low accumulation of irradiation. On the opposite side, we could see that iron was a bit, it was stable for a bit longer in the semi-pilot scale. Regarding results with the real secondary effluent, fortified secondary effluent in lab scale, we could also see the same pattern of degradation of contaminants, but we can see that the reaction time for degradation of these contaminants is longer, 50 to 60 minutes, with a high accumulation of energy required. Regarding the efficiency of removal, all of them presented an efficiency higher than 80%, and also iron in the secondary effluent is it's present it requires a high accumulation of energy, and this is due to the presence of different components of the effluent matrix, which contains organic matter, organic compounds, inorganic ions. And also, during the treatment, we can form different substances from degradation of the compounds, of the matrix and the contaminants, such as carboxylic acids, phenolic groups, and all of them can have an impact on the efficiency of the reaction. Usually, we can see more inhibitory effects from the organic matter and inorganic ions than promoting effects. Thus, explaining the slowing down of the reaction in the secondary effluents compared to natural water. Considering the results without fortifying the effluent with the presence of the contaminants in this effluent detected by mass spectrometry, we could see that the 3 milligrams per liter in green, with and without the aluminum surface could not achieve the 80% of removal proposed by Switzerland legislation, around 65% of degradation only, and only with a higher iron concentration, comparatively higher in this way to the 3 milligrams per liter, we could achieve over 80% removal. Again, we could see a longer treatment time and higher accumulation of energy required in the real secondary effluent, in real conditions for the treatment of the contaminants. In this way, with conclusions from this chapter, we could see that indeed, solvent iron concentration and liquid depth are major parameters in the solar photo-Fenton reaction. And the reaction would stop or slow down when the concentration of solvent iron would be too low, meaning that the complex was completely decomposed and there was no more EDDS available to complex the remaining iron. Also, we could see that the aluminum reflective surface was noted more with enhanced effect in lower iron concentration due to with a lower iron concentration in just water, in natural water, there is a reduction in the light attenuation effect of the ions itself. Finally, results with a lower concentration fortified in the effluent are closer to results in concentrations detected in real wastewater treatment plants. So whenever, if possible, we should work at lower constant fortification concentration of contaminants. And reactions were slower in the real effluent due to the presence of organic matter, turbidity, and other components of the real matter, and this would slow down the decomposition of the complex, the decomposition of hydrogen peroxide consumption, and finally we could achieve a treatment time of 6 minutes to achieve the 80% removal of contaminants using 0.1 millimolar of iron, 5.5 milligrams per liter. With all these results in mind, we moved on to chapter 3, on which we executed this modified circumneutral photo-Fenton reactions to evaluate both removal of CCs and finally disinfection in a real secondary effluent from a combination of anaerobic and aerobic system. So the objective of this chapter was to evaluate the removal of our selected contaminants, our 6 selected contaminants, evaluating for disinfection both E. coli and total coliforms in this WASB, upflow anaerobic sludge blanket reactor, followed by a combination of trickling or biofilters made from a sponge bed component. These demonstration scale reactors are found in Belo Horizonte City in a center for research on wastewater domestic treatment. We collected and proper storage these effluents before a complete characterization in the laboratory at the university. And this time we needed just a pretreatment of prefiltration, which we used stainless steel mesh filters to achieve a almost similar removal efficiency of turbidity as in the chapter 2. And there was no need to perform a partial removal of carbonates as in the first stage, because for this kind of effluent from an aerobic reactor in biological filters, we could achieve a low alkalinity and low inorganic ion concentration. Also, in this effluent from this kind of reactor, in Brazil, in the Belo Horizonte city, we can see a low conductivity and concentration of inorganic species. And we choose an evaluation of an aerobic reactor followed by a biological filter, since it is a configuration very common in Brazilian municipal wastewater treatment plants around the country. These reactors, WASB reactors, can also be found alone or in combination with stabilization ponds. For the evaluation of the selected CCs, we used HPLC coupled to a DID diode array detector from Shimatsu. We also performed the calibration curves as well. And we performed the experiments only in lab scale this time due to restrictions of pandemic just last year. And we performed the experiment in also a solar chamber with a different model from Atlas. We used glass reactors this time. We performed the experiment just at the highest possible liquid depth of 10 centimeters with 1:1 concentration of iron, and also with the irradiation set to 30 watts per square meter, a normal sunny day at noon. And we performed the experiment with spiked and not spiked effluent at 100 micrograms per liter of each compound to evaluate the effect of the fortification on the disinfection process. As results from this chapter regarding the removal of our selected thesis in the effluent at 100 micrograms per liter, we could see again the degradation pattern, with diclofenac being the first one to be degraded and caffeine the most resistant one. This time we encountered a longer treatment time for the removal of contaminants and a higher accumulation of energy necessary at lab scale. We could achieve in red here in the graph, over 86% of degradation for the sum of contaminants with the photo-Fenton reaction, while no degradation, almost no degradation during photolysis in blue, and just a small degradation during photoperoxidation in green, 14%. Regarding the hydrogen peroxide consumption and iron results in the secondary effluent, we could see a high consumption of hydrogen peroxide, especially in the fortified effluent with complete consumption, almost no consumption during hydrogen peroxide peroxidation, as expected for a solar reaction with short time in a non-concentrating reactor. The iron was the pattern was also the same, with iron stable just for for the first hour, and after the decrease in dissolved iron concentration is when the consumption of hydrogen peroxide stabilizes with a higher concentration of energy again. Finally, for the disinfection results in the secondary effluent, we could see almost no removal of both total coliforms in the left in blue, and for E. coli, we had just 1 log of removal during the control of photolysis. While when applying the photo-Fenton reactions, we could achieve a higher removal of about 2.5 removal logging units of total coliforms, and also around 2.5 for E. coli. We could not see a great difference among the spiked and the non-spiked and the spiked. The triangle is the spiked one, and the square is the non-spiked effluent. And we need further experiments, further investigation to evaluate this with also other species. Regarding the photoperoxidation, we could see a higher log removal of total coliforms and the same log removal of E. coli than the photo-Fenton reactions. And we need to remember the different mechanisms of disinfection for this bacteria that have been widely investigated in the literature, and how the disinfection process itself is mainly by for example, the internal photo-Fenton reactions, and with the addition of the concentration of hydrogen peroxide, we can enhance this process. Finally, considering the residual levels of pathogens in the effluent, there is a reuse possibility for less strict requirements, up to 1,000 most probable number in 100 milliliters, which do not involve a direct contact with human for ingestion or even handling of this effluent for other kinds of use, for example, irrigation and landscaping. In this way, with chapter 3, for our conclusions, we could see that the modified iron DDS complex photo-Fenton reaction was indeed efficient for the removal of the sum of the contaminants, with over 80% of removal, and also we achieved a high removal of total coliforms and E. coli, with about 2.5 log units removal of each one. Regarding the photoperoxidation reaction, it is efficient for disinfection, but it was not able to remove efficient contaminants. So this treatment could be used, can be used as shown in the literature in combination with different setups to make the most of both of them and try to reduce, for example, the treatment time. And finally, the residual levels of pathogens in the effluent could allow several reuse applications with less strict requirements. For example, urbanistic and agricultural use that do not involve irrigation of, for example, lettuce and this kind of food that you do not ingest as raw. As the conclusions of this thesis regarding our initial literature gap questions, most studies, they indeed don't show the simultaneous information on removal of CCs in disinfection when we analyze effluents from municipal wastewater treatment plants being treated with any kind of advanced treatment. And also, we saw from chapter 1 that most studies, they either focus on aerobic or just conventional activated sludge biological treatments. Regarding the second guiding question, we could see that the use of the aluminum reflective surface could improve the photo-Fenton reactions using a low iron concentration in the open solar photoreactor, but we also saw that this would be more indicated for less colored with lower turbidity wastewaters, or using a lowering down the liquid depth to achieve a proper optical depth for the reaction. And as for chapter 3 and the last guiding question, we could see that the circumneutral photo-Fenton reactions are as well efficient for the application in a different kind of effluent from a different biological treatment. For example, a combination of anaerobic and aerobic was the upflow anaerobic reactor with a trickling filter for both disinfection and removal of CCs. And after this work, we can make some recommendations, including in chapter 1 with the bibliometric analysis for the application of this methodology. We added at some stage of this methodology, we suggest also to add relevant recent publication papers published, more recent, but which they had few citations. They can also be very relevant to the research as we saw. Also, regarding the application of the aluminum surface, this should be investigated in a continuous operation to evaluate both costs in the reactor and also the durability of materials. Regarding the anaerobic, the test in the chapter 3 with anaerobic effluent, we propose an investigation at lower MEP initial concentration, and to also evaluate the direct treatment of the effluent without the prefiltration, since there is a low turbidity in this effluent. And finally, other recommendations are the evaluation of different hybrid systems, including different configurations of wastewater treatment plants in Brazil, and to evaluate, for example, different mixing design of the RPR reactor, which we wanted to do but could not achieve in this work, which can allow, for example, an intermittent or sequence dosing of iron. And finally, the evaluation of specific bacteria and pathogens, which are the antibiotic resistant bacteria, very relevant nowadays, and the formation of transformation products during this work. So here are some of my reference during this presentation and the work. And I would like very much to thank, I know that I couldn't show everyone, but I hope I showed most of people. I'd like to thank my friends from Grupo since forever in the Federal University of Minas Gerais. Muito obrigada a todos. I'd like to thank my advisor from a long time, Camila also. Muito obrigada. And also I would like to thank the team from the Plataforma Solar of Almeria. Muchísimas gracias a todos los compañeros de Almeria. Y also my co-supervisor, Dr. Sixto Malato. Thank you so much. And finally, I'd like to thank my family. Muito obrigada. E é isso. Muito obrigada a todos.
Thank you so much, Elizângela. Congratulations for your presentation. It was very good. And thank you for the acknowledgement about everyone from our research group and about me as well. I don't know if you want to have sometimes to have water or to go have a break, or we can continue. What do you think, Elizângela? You want like 5 minutes or something? No, we can
go.
Okay.
I'm gonna just
go
stop sharing.
No.
Or I stop sharing or?
Yeah, I think that you can stop sharing. Yes, it's better. We can each other. We can watch it. Okay, thank you. So now we are starting the discussion, and then I would like to invite Professor Carla to start this part of the thesis, and I want to say thank you again, Professor Carla, to accept our invite, and please feel free to do your contribution, okay? Carla, I don't know if you are more comfortable to say in Spanish. You could ask in Spanish because Elizângela could talk in Spanish and Sixto, of course.
You
and
can
then
correct me.
If you want, we can talk in Spanish, okay? In español.
Okay, thank you, Camila. Okay, in Spanish?
Oh, I'll try. Estoy un poco sin prática. Tengo que entrenar más, pero vamos.
But if you have some doubts, Elizângela, Carla could say in Portuguese. It's fine.
Yeah, or in English, or in the three languages. Okay.
Como lo quieras.
Bueno, pues buenos días a todos. Muchísimas gracias, Elizângela, Camila y Sixto, ¿no? Por esta oportunidad de leer tu tesis y de estar aquí en tu presentación, ¿no? En tu defensa. Y también a los compañeros, a profesor Alan, Thiago y profesor
Carla, you are speaking in Spanish.
Oh, yes. Muchísimas gracias, ¿no? Y espero que estés bien. Y bueno, voy a poner algunas, yo creo que son comentarios generales, pero que vosotras podéis intentar, ¿no? A ver si es necesario cambiar o a lo mejor poner algunas de las cosas que yo he comentado, ¿no? He intentado poner más de mi parte, de lo que yo entiendo que sé un poquito más, ¿no? Y sobre todo con el intento de mejorar, si es posible, todavía más tu trabajo, porque yo creo que la tesis está con una calidad muy, muy alta y realmente es muy relevante, ¿no? Para lo que es la temática que os habéis propuesto estudiar. Entonces, en este caso, también enhorabuena, ¿no? Por la tesis y por la presentación. Bueno, me gustaría comentar algunas cosas y yo creo que el corazón de tu tesis, sobre todo, ¿no? Al leerla, yo entiendo que es sobre todo el intento de mejorar todavía más, ¿no? Lo que es el reactor, el raceway, ¿no? Y creo que habéis tenido muchísimo éxito, ¿no? Con lo que habéis pensado y planteado y realizado, ¿no? Como ensayos ahí. Y también creo que entiendo, ¿no? Desde mi punto de vista, que tu tesis también está muy bien diseñada en el sentido de que empiezas ya en el capítulo 1 con una revisión y una revisión sistemática bastante amplia de lo que es la temática que después, ¿no? Te dedicas a estudiar con más detalle. Esto yo creo que es muy interesante y muy importante porque en el documento general eso se queda como una revisión, ¿no? Bastante amplia que fundamenta, que pone realmente cuáles son los puntos débiles que es necesario mejorar, que es necesario estudiar en el área, ¿no? De interés en que está tu tesis. Entonces, yo creo que está muy bien la estructura y también la idea del capítulo 1. Además, yo en especial, ¿no? Después de leer de participar de tu examen de cualificación, ¿no? Y, me interesé muchísimo por esta herramienta, ¿no? Que es el análisis sistemático, porque de verdad hace con que se pueda hacer una búsqueda mucho más dirigida. Además, trae, ¿no? Algunas cosas muy interesantes que yo creo que nosotros del área más técnico, sea de ingeniería, química, no tenemos tanto manejo de esto, ¿no? Como el post-viewer, las presentaciones, ¿no? Sea de las palabras clave, sea de los autores, sea de los journals. Yo creo que todo esto sí es muy interesante, muy importante y yo creo que en la parte más técnica todavía no es tan empleado como a lo mejor podría ser, ¿vale? Entonces eso también es un punto clave y un punto extremadamente positivo de tu trabajo y de tu tesis. Entonces también enhorabuena por eso. En especial en el capítulo 1 me llamó muchísimo la atención la tabla 1.4.6 que está en la página 58, porque yo creo que esta tabla es una esencia, es un resumen, pero muy bien detallado de realmente lo que son los aspectos que tu tesis va a tratar, va a traer y realmente los retos que hay, ¿no? Por superar. Entonces, me llamó mucho la atención y creo que está muy bien estructurado y en concreto esta tabla. Bueno, además, en la página 63, ¿no? Hay ahí una frase que pones, ¿no? En que tú comentas respecto a las eficiencias de remoción de algunos de los compuestos, ¿no? De los compuestos modelos que tú has elegido trabajar, ¿no? Y entonces, en este caso, cuando yo he leído esto y considerando, ¿no? Que mi formación es de química en química y química analítica en concreto, yo no sé si a lo mejor tú también tienes esta impresión, pero la cuestión es que muchas veces, muchísimas de las remociones, ¿no? De las deficiencias de remociones que están puestas ahí van casi al 100%. Pero hay un punto que yo entiendo que es quizá una debilidad, porque en el área en que trabajamos es un área que yo entiendo que es multitransdisciplinaria, y entonces hay realmente muchas personas de distintas áreas que hacen el trabajo. Y ahí me pregunto, ¿no? Si quizás en algunos de los papers, y en la mayoría de estos papers, por ejemplo, las figuras, ¿no? Las figuras de mérito, los parámetros de performance de todo el método que se ha utilizado para cuantificar estos analitos, si esto está puesto o no.
No. En un ejemplo que en el caso del análisis bibliométrica, el análisis temático, algunos papers yo he visto que no tenía todos estos parámetros del análisis. Un ejemplo, algunos son como un sumario, un resumen de todas las informaciones de eficiencia, de remociones, y solo esto, no hay muchos detalles de todos los parámetros de investigación.
Claro, porque esa es la cuestión. Cuando tú pones que tú has tenido una eficiencia de 100% en la remoción, ese 100% no es verdadero desde el punto de vista de la química analítica. Pues tú has llegado al punto, ¿no? Del límite de cuantificación que tiene tu método, y entonces después por debajo de esto ya no puedes hacer una cuantificación. Entonces, claro, se pone 100% porque después se hace la relación de lo que había al principio, y por porcentaje eso ya es como que si se eliminara este punto, ¿no?
Sí.
Quizá. Entonces, esa es una cosa que yo creo que no es una crítica a tu trabajo, pero es interesante porque, claro, cuando se lee un paper, pues puede que los autores hayan pues, pues nosotros conseguimos 100% de remoción o 90 y unos pico por ciento de remoción de casi todos los compuestos, pero claro, la cuestión es esta, ¿no? Es cómo está ocurriendo esta cuantificación, cómo es tu método. Entonces, esa es una cuestión que yo todavía creo que las personas que tienen formación en química analítica y mismo los ingenieros, pues toda la gente que trabaja en este área, yo creo que en este caso tiene que poner un poquito más de ojo. A lo mejor no es decir 100% de degradación, es decir que está por debajo de tu límite de cuantificación y punto. ¿Vale?
Perfecto.
Y además no hace falta que tú tengas el mejor equipo para hacer la cuantificación, no, porque eso también no es posible, ¿sabes? Pero yo creo que sí, eso es una cosa que tenemos que madurar un poquito más a la hora de presentar los datos. Eso sí, yo creo que se queda aquí como quizá una sugerencia colectiva de los que trabajan, porque yo creo que sí, es una cuestión que yo creo que tenemos que poner en la mesa porque es importante. Bueno, después, respecto al capítulo 2, yo creo que este capítulo está realmente con una calidad muy, muy, muy alta, y eso, por supuesto, que se refleja en las dos publicaciones que tú has tenido, ¿no? Y realmente yo creo que ahí está el corazón de tu tesis. Enhorabuena por los estudios y por haber trabajado tanto en el periodo que tú has estado ahí en Almería. Yo sé que realmente, como yo he tenido mi formación ahí, sé cómo funciona, sé cómo es en general la dinámica, y yo creo que es muy importante tener esta experiencia también, porque ellos son excelentes en lo que hacen, y yo creo que sí, este intercambio y esta forma de aprender y aprender a hacer las cosas de una forma distinta, muy profesional, entiendo yo, creo que está muy bien. Y la idea de mejorar lo que es el REST-Way, yo creo que es excelente, ¿no? En este caso, por esos dos trabajos. Entonces, ahí yo veo que está realmente muy bien, muy bien, muy bien. Bueno, respecto al capítulo 2, he encontrado solo he echado de menos a un parámetro, ¿no? Que es justamente el límite de cuantificación en la tabla 2.3.2, en la página 95.
Otra vez.
Y es que yo...
que tú has apuntado en el examen de calificación y me he olvidado.
Ah, pues mira, no, yo no me acordaba de eso, pero eso sí, porque además me llamó muchísimo la atención porque en el párrafo que está, ¿no? Inmediatamente por arriba de esa tabla, tú
Ay,
dices
sí.
incluso que
Sí.
va a presentar el límite de cuantificación. Entonces yo me quedé ahí y digo, que a lo mejor el límite que está puesto, ahí está puesto como límite de detección, pero quizá fuera el de cuantificación, no sé. O no sé lo que ha pasado. A lo
Não,
mejor se te ha olvidado.
hace falta añadirlo el límite de detección o de cuantificación, perdón, sí, y lo voy a buscar estos datos con Sixto y en la PCA otra vez.
Vale,
Los
perfecto.
hace falta.
Sí, es que son tantas cosas que a lo mejor pues a uno se le olvida también alguna cosa.
Sí.
Y también está bien porque así puedes decir alguna cosa, porque si no es que claro, con un trabajo cuando está muy bien se quedan pocas cosas y hay que coger así con pinza una y otra cosa porque es difícil, ¿vale? Entonces eso también a mí me ayuda en este momento. Bueno, pues siguiendo. Respecto al capítulo 3, ¿no? En la tabla 3.1.2, que trata sobre las comparaciones, ¿no? De los efluentes secundarios, de la calidad, de los principales parámetros macro, ¿no?
Sí.
Que hay en Brasil y en comparación con lo que hay en España. A mí me llamó muchísimo la atención porque se observa, ¿no? Se queda muy claro de que son efluentes secundarios y en algún caso pues puede que hayan pasado por algún sistema de tratamiento que es muy parecido, pero las características en general, ¿no? Algunas más o menos se mantienen, pero hay algunas que son muy distintas. Y claro, eso es esencial, ¿no? Ese punto de caracterización, ¿no? E incluso de comparación, porque tu experiencia ha sido en el capítulo 2, tus resultados con lo que es el efluente de España y ya después con lo que en el capítulo 3 es el efluente de aquí de Brasil. Y cambia, porque es una matriz que no es igual, que es distinta y claro, los retos y cómo el proceso, cómo el tratamiento va a tener lugar, pues eso también a lo mejor no es tan influenciado, pero en parte sí. Entonces, claro, eso es muy interesante y muy importante. Bueno, después, mi última pregunta respecto a lo que es tu tesis y al capítulo 3, ¿vale?
Vale.
Una observación en la tabla 3.3.2 en la página 161, ¿vale?
Vale.
Ahí en esta tabla, tú pones sí el límite de cuantificación, todos los parámetros, ¿no?
Sí.
De performance del método, pero hay una cuestión que me gustaría solo a lo mejor comentar un poquito. Me parece muy raro que tu límite de cuantificación, ¿vale?, esté por debajo de lo que es el rango lineal de tu método, porque tú ahí pones que el rango lineal, si no me equivoco, es de 10 a
sí.
120,
20.
Sí,
120 en esto.
microgramo litro. Pero claro, cuando tú pones ahí los límites de cuantificación, hay muchos que están por debajo de 10, ¿vale? Pero eso, yo leyendo, creo que es por cuenta de cómo en general se hacen los cálculos para determinar el límite de cuantificación en el área de cromatografía. Entonces, en general, lo que se hace, se coge la señal y el ruido, entonces 3 veces esta razón, ¿no? Esta relación y 10 veces. Y ya está. Pero eso no está mal, es así que se hace y eso, vamos, de toda la vida. Pero lo que pasa es que cuando tú, al calcular esto, que es matemática, ¿no? Hace y obtiene un valor que está por debajo, ¿no? Del punto más por debajo de tu recta de calibrado, entonces creo que es conveniente en este caso. Nosotros aquí lo que hacemos es poner más puntos más abajo para intentar ampliar este rango lineal y entonces que tu límite de cuantificación esté, ¿no? en este rango
El
lineal.
rango lineal. Ah,
Claro.
vale. Yo no lo sabía.
Sí, porque,
Sí,
claro,
pues.
porque si no, tú dices que lo que es el rango lineal es que tú estás teniendo una respuesta instrumental ahí, que en este caso debe de ser el área, ¿no? De tu pico
Sí,
cromatográfico, que es proporcional a la concentración de tu analista.
perfecto.
Pero eso, ese rango lineal es donde hay una proporcionalidad entre eso.
Sí.
Pero si tú estás haciendo la cuantificación por debajo, puede que, y en general es lo que pasa, si se hacen muchísimos puntos, cuando se construye esto, hay una cuestión de un límite instrumental. Entonces, por debajo, tú vas a ver un sistema donde va a haber muchos puntos por debajo así, cuando llega a obtener este rango lineal y ya por arriba donde también sigue teniendo puntos, ¿no? Donde ya tú no consigues tener esta respuesta lineal. Entonces, por eso yo creo que ahí quizás es conveniente, ¿no? Volver y probar estos puntos más por debajo para que yo entiendo que tenga lógica y que tu límite de cuantificación, ¿no? También esté ahí en esta franja donde tú haces el rango lineal.
Perfecto. Lo haremos así que posible.
Sí. Bueno, pues nada, por lo demás, enhorabuena de nuevo por la presentación, por el trabajo. Creo que las conclusiones y lo que ponéis como quizá, ¿no? Etapas futuras, que a lo mejor pues te puedes tocar aquí, si a lo mejor sigues haciendo un postdoc o quizá pues ya regales, ¿no? En lo que son estos retos a otro compañero que venga ahí, ¿no? A la maestría o al doctorado. Y yo creo que está muy bien puesto y se observa que sí hay una construcción de un trabajo con lógica, ¿no? Y en un área donde realmente es necesario mejorar y donde hay muchísimas cosas por hacer, pero yo creo que dentro de lo que es el área de actuación, ¿no? Que vosotros tenéis, pues está muy bien puesto y entonces también enhorabuena por eso. Pues nada, esta era mi contribución. Muchísimas gracias. Enhorabuena, Elizângela, sobre todo.
Yo que agradezco muchísimo.
Y ya está. Gracias.
Thank you, Carla. We appreciate your contributions. I think that Elizângela did everything that you said the last time in the pre-thesis. Then we know here qualify, but I don't know if these terms exist in the abroad. We forgot these small things in the LED and LED detection and quantification, but Elizângela will correct that. And of course, the last chapter, it was very, very, how can I say, damaged. It's not damaged, but interrupted because the COVID pandemic. It's a situation for everyone, it's not for us. Elizângela was planning to do more things, but we have to stop the things because the COVID restrictions. And we know in our institutions, it was very, very difficult because we was not allowed to go to the labs and to do. And when we collected effluent samples, real samples, it's more difficult because we have some risks involved with the COVID and other things. So we have to stop the things. But I think that in the final, we are having a very good work, and hopefully Elizângela could continue the small things like the polish of the things with, of course, the contributions of this judge. Because Elizângela will be our postdoctorate research in our research group. So Elizângela will continue with us, hopefully for a long time. And thank you again.
Thank you.
And now Sixto, want to say something? If everything's fine for you?
No, thank you. I am very happy with Elizângela's work.
Okay.
And the comments of Carla has been very pertinent. I know that we have this information about limit of quantification because we want to always to try to be confident from an analytical point of view. We are mainly chemical engineers, but we try to be confident in analytical part. And okay, I think that Elizângela will correct it without any problem. So,
okay.
No comment
Thank
from
you.
my part.
And now we want to invite Professor Alan Trovó. Please feel free to do your contributions, and thank you again to accept our invitation. We are without...
Eu que agradeço a professora Camila, a Elizângela, pelo convite, pela confiança e pela oportunidade de colaboração. Quero dar os parabéns à professora Camila, ao Sixto e à Elizângela pelo excelente trabalho, assim como também a Elizângela pela apresentação, excelente. Peço desculpa aí ao Sixto, eu pedi anuência para Camila para falar em português, me sinto mais à vontade, mas se houver aí alguma dúvida, a gente tenta esclarecer. O trabalho está excelente, gostei muito da estrutura, e é notório aqui, que você trabalhou intensamente, Elizângela, fruto disso aí que você já tem 3 publicações, em excelentes revistas. Acho que você começou muito bem, fez todo um levantamento bibliográfico, aí uma parte sistemática, adotou critérios para redigir um artigo de revisão. E aí, com base nessa revisão, então você fez a sua parte experimental. Então, eu não tenho nada a comentar sobre o primeiro capítulo, tá? Eu anotei aqui, algumas observações, e são mais, assim, curiosidades. Na página 87, você comenta em vários momentos do texto sobre a importância de se utilizar a radiação solar, visando a redução de custos. E o que me chamou a atenção, por exemplo, que o objetivo foi trabalhar em pH próximo à neutralidade. Se nós pensarmos numa aplicação, eu gostaria de saber, tipo, a motivação da escolha desse ligante, porque se a gente for pensar em aplicação e considerando, aí o fornecedor, a Sigma Audit, se nós acessarmos o site da Sigma Audit, o custo de 1 litro desse reagente, que é 35%, no Brasil hoje ele custa R$ 4.627. Se a gente, então aí daria o quê? 350 gramas desse valor. 1 quilo daria R$ 13.000. Se a gente pensar, que foi feito aí a contextualização em termos de redução de custo, como ficaria essa parte em relação ao ligante?
Então, professor Alan, com relação ao ligante, né, sim, né, temos consciência desse preço elevado, né, do reagente laboratorial, mas pensamos também no futuro de aplicação eu não sei te falar um valor, eu posso conferir, para adicionar isso na tese, né, um valor se temos em escala, ou um reagente com pureza, não pureza para análise, né, laboratorial, mas um para aplicação em larga escala, né, um reagente mais comercial. Eu creio que sim, porque em alguns artigos é mencionado, né, a aplicação dele em substituição ao EDTA, não somente, né, nos trabalhos com foco, né, no tratamento, né, do photo-Fenton a pH neutro, mas como um substituinte mais biodegradável e de menor impacto ambiental que o EDTA. Posso verificar e tentar adicionar, né, levantar essa discussão na tese. E com relação a essa aplicação, essa análise de custo, tem até um trabalho, não sei se é de 2020, também da equipe do pessoal em Almeria, que eles comparam tem um artigo da Paula que ela compara essa aplicação, os custos com sulfato ferroso, né, e faz com ferro EDDS, e ao final, devido à eficiência, a menor utilização, menor concentração e a redução de custos com a neutralização e neutralização dos carbonatos, né, com toda essa parte com a economia com o ácido sulfúrico, eles acabaram atingindo um desempenho, né, isso em escala, mesmo com os valores da escala laboratorial para esse reagente, se eu não estou enganada.
Okay. Se quiser responder em inglês ou espanhol, pode ficar à vontade, Elizângela.
Okay.
It's just for Sixto knows about the response, okay? If you feel more comfortable, and then I think that these questions should be okay, but the next one, okay, Elizângela?
Ok.
Mas, por exemplo, existe que nem uma outra possibilidade também seria testar, utilizar outros ligantes mais baratos.
Oh, yes, of course. Regarding the chelating agents, I think we tried to focus in just one during the work, initially because we tried to focus in this one that had already been under investigation. And I've seen also regarding different chelating, a good efficiency for EDDS, and in comparison, for example, and the pH, if I'm not wrong, we can work with higher pH, for example, in comparison to citrate or others or the ferrioxalate that you work around 5 in the pH sometimes.
Assim, o que tem que, de repente, o citrato e o oxalato, você precisa usar um excesso bem maior, né, quando comparado ao EDDS.
Oh, yes, also the rate of application of the chelating and iron sometimes can be higher for others. And for EDTA, NTA, and other aminopolycarboxylic compounds, I think you can have in EDDS, DTA, a lower ratio. And this is very important also to not add more organic content to the effluent. For example, with the EDDS, we tried, and the literature also, many people tried to reduce the ratio of iron and the chelating to not add excessive carbon to the effluent, since we are trying to treat this effluent. I have worked only with the 1 to 2 ratio of iron in EDDS to make sure to have an excess of EDDS to keep this reaction as efficient as possible. But I wanted to do to chapter 3 with also a ratio 1 to 1 that has been showing also many papers to be as efficient, but we did not have the time to. And there are recent published papers with this 1 to 1 ratio of EDDS.
Ok, thanks. Na página 93, né, na figura 3.7, né,
Yes.
onde você apresenta aí a porcentagem de recuperação, né, com os cartuchos utilizados para cada contaminante, né? A minha curiosidade é, existe alguma variação aceitável aí? Né? Se chegou a procurar algo, por exemplo, se aceita, que nem tem algum que varia aí de 100 a 30, né? Tem uma variação de 30. Outros, né? Teve uma variação de 10%, né? Outros de 20%. Por acaso você chegou a procurar na literatura qual seria aí, né, um delta aceitável em relação ao nível de concentração que você está trabalhando?
I have to be honest, I haven't looked for a specific for this part, but I've seen in general around a variation from 80% to 120, something about that, of variation for recovery in solid phase extraction. But regarding as the level of my contaminant, the concentration of the contaminant, if this reaches this variation, except I have to be honest, I haven't looked. I could add this.
E quanto menor a sua concentração, né, geralmente é maior essa variação aceitável. Não, eu só estou falando isso que de repente, né, se tem a possibilidade de melhorar, depois você discutir um pouquinho mais essa parte, né, e citar referência para, né, mostrar que essa variação aí está dentro do aceitável, ok?
Okay, I will add this information also in discussion.
Também, essa mesma observação que a professora Carla comentou sobre o limite de quantificação, né? E eu acho que talvez seja coerente aqui na página 94, né? Citar como foi obtido, né? Ou como foi determinado os limites de detecção e quantificação, né?
Okay.
Foi pela curva, foi pelo método visual, sinal ruído, né? Então, porque da forma como está, se alguém quiser reproduzir o seu trabalho, ele não tem essa informação, né? Então, lembre-se que esse é um documento, né, que vai ficar na biblioteca, que outras pessoas podem utilizar ele para num trabalho futuro. Tá bom?
Okay, I will look with Sixto this information, and we add the methodology and the result of the limit of the quantification, that is the one missing.
Daí, na página 95, né, nessa tabela 3.2, né, o que me chamou aqui a atenção, eu entendo que é um UPLC, né, mas que nem quando você tem ali os compostos, né, o tempo de retenção, por exemplo, do acetaminofém para cafeína, dá mais ou menos, né, 1 minuto. Só que entre a cafeína e a carbamazepina, dá 0,3 ali, a diferença, né, do tempo de retenção. Eu gostaria de saber se em termos de resolução, houve uma boa resolução, eu acredito que sim, porque é um UPLC, né? Ou se houve coeluição aí entre os picos.
No, not in general. There was not I'm sorry for everyone. I'm just saying that I've made a mix up with this table, and I've mixed up the trimethoprim with carbamazepine. They are in the incorrect order. I'm gonna correct this. I'm sorry. And regarding this coelution possibility, no, in fact, there was not. There was a good resolution. We could see each compound, even though with a short difference of time between them. And no, I don't know if I could add a chromatogram or something, but I don't know if I have one from this.
Talvez depois, né, o que você poderia fazer para ficar mais ilustrativo, pegar um cromatograma e inserir aqui, que aí você mostraria, né, que houve sim uma boa resolução, porque essa mesma dúvida que eu fiquei, um outro leitor pode ter, né? Já que do acetaminofén para cafeína tem um minuto, né? Da carbamazepina para o diclofenaco também dá um tempo de 1 minuto ou mais entre os outros compostos. Então depois é só extrair um cromatograma e colocar aí, porque aí fica mais nítido, né, visualmente, que não houve essa sobreposição aí das bandas de dois compostos, né?
Okay, I'm gonna look for a chromatogram for this and also for chapter 3.
Elizângela, you want I can explain something more because you don't mind. It's possible?
Yes, of course.
Yes, it's better you add the chromatogram, but I only trying to explain that in UPLC, in ultra performance liquid chromatography, the typical retention time always have lower because of it is ultra performance. Huh? So the separation of the peaks could be smaller than in classical HPLC. So I have to say that really the separation that you have with UPLC is a high separation for UPLC.
Yeah.
Because of it, because it's a ultra performance. So everything is done in the peaks are longer and more and less wide. So the classical separation of 1 minute in the case of UPLC could be 0.3, 0.4 minutes without no problem.
Okay.
So in general, I think that you add the chromatogram that is asking for alarm is more clear. But the main advantage of UPLC is that you have all the peaks in less time because everything works higher pressure, higher retention of the column. Everything is quicker and a little bit more expensive because you spend more solvent. But the general result is that you do everything quicker.
Okay, thank you.
Daí, indo para a página 102 e 103, opa, 103 e 104, né? Você fala que foi feito ali, né, a adição do ácido sulfúrico para reduzir a concentração de carbonato, bicarbonato. Nessa tabela 3.5 e na tabela 3.6, né, essa caracterização apresentada é antes da adição do ácido sulfúrico, né?
Yes, it's before the addition of the sulfuric acid to also to prove the need to do this partial neutralization, to see that the natural water, as we initially got it, it had a high content of inorganic carbon. But after the adjustment, it was around 50 milligrams per liter.
Ok, né? Você tem aí que você, ajustando o ácido sulfúrico, você chega aí a 15 miligramas por litro do carbono inorgânico. Mas não seria interessante apresentar também uma terceira coluna com resultado aí? Por quê? Para saber, né, se houve alteração do pH, para saber o que em termos da concentração do sulfato, já que você, ao adicionar sulfúrico, você está adicionando sulfato, né? Então, qual seria aí a nova concentração de sulfato? Porque, eu não sei, aqui eu cheguei a fazer uns cálculos, né? Que nem para... Vamos pegar aqui, de 212, você reduziu para 15 miligramas de carbono inorgânico, né? Teve uma redução de 197 miligramas de carbono inorgânico, o que equivale a 1.000 miligramas de bicarbonato, né? Considerando esse pH aí 7,4, o carbonato está majoritariamente na forma de bicarbonato. Se a gente pegar ali, né? Um bicarbonato, então, né, ele vai aceitar um próton, ainda ácido carbônico, né? Por exemplo, 61 miligramas para 1, então 1.000 daria 16 miligramas de H+, que precisaria. E isso, então, daria o que? Uma adição de 784 miligramas de ácido sulfúrico, o que corresponde, então, a 768 miligramas de sulfato adicionado, né? Mais ou menos.
We did not perform for chapter 2. I tried to do this after in chapter 3 to analyze the onions as what I could analyze of onions in Brazil. I tried to see the increase in sulfate. In Brazil, it was not much. I don't know if you saw in the chapter 3, but for these results in chapter 2, I don't have the sulfates. I don't know if Sixto has information on other work.
Yes, I have this. In other words, we have the information about that. I don't remember quite well, but it's something around 140 milligram per liter of sulfate. I have not in my mind, but it's in the range of 150 milligram per liter. This is I have in my mind other tests. Only to clarify one matter. We have been talking about reduction of carbonates, in this case are bicarbonates and so on, but we have to point out that the groundwater that we have here at PSA is especially wrong. It's not groundwater that is permitted for example, as potable water. So this is a very special situation because our tap water, our groundwater is very, very, very bad. For example, if you can compare with other analytical of water in other area of Almeria, in other part of the world, the concentration of carbonates is more than five times more than the usual. So this is a very special situation about that. So we know that to remove carbonates is not very recommended, but in general, in many cases, you don't need to remove carbonates because the content is low. And in the general condition of municipal wastewater that come from water that was potable, the quantity of sulfuric is very low. Okay. It's a very, very special situation provoked by how the low quality of our groundwater here at Plataforma.
Yes, and over here in Brazil, we didn't have this problem because we don't have the same conditions, the same quality of water than in Spain. So over here, we didn't use this acid, sulfuric acids for this.
Yes, in general, Camila and other people, well, I know that perhaps this answer is not possible to be answered by Elizângela. What we are developing is methodology, not solutions. It's methodology of how to solve. For example, you have a water with very high content of bicarbonate. Do not use advanced oxidation process in general. This will not be a solution. So we are developing methodology, not a solution that could be used everywhere in any moment.
Of course.
This is the main idea. The main idea, perhaps for a PhD student, is not so clear, but we have different studies of other papers where we are talking about which is the logical limit to be applied in the case of photo-Fenton and neutral pH as function of bicarbonates.
Yes.
And so this is what I mean, is that we are developing methodology, but not industrial solution based on a thesis. This thesis is provoking methodology that we have in our hands for a study later each case. In the case of Elizângela, she suffered from the low quality of our groundwater.
Daí, Elizângela, se houver a possibilidade, não sei também se vocês acharem coerente, né, de acrescentar uma coluna aí ao lado só para mostrar. Eu acredito que não deve ter ocorrido uma variação no pH, porque você tem um tampão aí com uma capacidade tamponante alta, né? Você tem, então o pH se manteve praticamente constante.
Yes, I have the results from the experiment. I monitored the pH and temperature throughout the experiment, and after this neutralization, removal of bicarbonate, there was not a much change in the pH. In fact,
o que deve ter alterado aí mesmo é só a concentração de sulfato, né? Então, se você tiver essa informação para colocar aí ao lado, acho que no meu ponto de vista, é coerente, né? Mas aí fica à vontade, é uma escolha vossa, né?
Ok, thank you. I will calculate and add.
Daí, uma outra curiosidade que eu tive também é que os experimentos no RPR, né? Vocês fizeram fortificando a solução com os contaminantes preparadas em metanol, né?
Yes, okay.
Aí a
But
minha
it,
dúvida aí o outro que foi feito em escala laboratório, vocês fizeram uma diluição em água destilada e a partir dessa intermediária que foi feita preparada a solução nos experimentos em escala laboratório, né? Quando vocês adicionaram ali metanol, também é uma fonte de carbono orgânico, né?
yes.
Então, né, seria pertinente aí também, no meu ponto de vista, né, apresentar qual o novo valor do toque.
Okay.
Né? Eu acredito que deve ter levado bastante aí a carga orgânica. Não?
No, not
Não?
in fact, no, it did not, because we, as a, how can I say, a procedure from the laboratories in Almeria, the preparation of a higher concentration in methanol, 2.5 grams per liter, you just add a small volume of the solution to the 90 liters in the RPR. So the addition of carbon is very small. It's not, I can add this value, I had it calculated, and also I have the values from the through the experiment. The addition is not so much.
Desculpa, qual foi o volume que você, por exemplo, no RPR foram 90 litros, né?
Isso. Aí eu adiciono um pouquinho, Alan.
36 mililitros, deu?
Não,
Não?
foi menos. Espera aí.
It's very, very low.
No, I added with the pipette. It was small. I don't remember right now, but I have this value in my experimental sheet.
Yes, I remember more or less you want, Elizângela. Yes, it's only because I think this type of things is better to clarify why. So what we do in general is to prepare a solution of 2.5 gram per liter of emerging contaminant in methanol. 2.5 gram per liter in methanol. Why we do that? Because this is the unique way to dissolve in a modern solution big quantity of emerging contaminant and to be stable. This is the idea. Later, when we dose in the raceway, the final total organic carbon is in the range between 20 milligram per liter for 100 microgram per liter, 20 milligram of carbon if you use emerging contaminant in the range of 100, to lower concentration of TOC. So really the range of TOC that we are adding to natural water is lower than the usual range of TOC that you can find in an effluent from a municipal wastewater treatment plant. So what we do with the methanol is to be very useful for experimental work, but at the same time we are providing an organic carbon that is lower than the usual organic carbon that is in an effluent. So we are provoking that the water is a little bit more similar to an effluent of the municipal wastewater treatment plant. This is the main intention. Of course, Elizângela, you could add this, but the value. But really, in the thesis, it's logical to add this data. But have in your mind that the main idea is because of practical reasons to be able to make experiments with a lot of emerging contaminant at the same time. Otherwise, it's impossible to dissolve the water.
Que eu cheguei a calcular aqui, acho que eu fiz alguma coisa errada, porque aí coloquei 2 milhões e 500, né, microgramas, né, que volume nós pegaríamos se o volume da solução final é 90 litros a 100 microgramas. E aí deu 36 mililitros de metanol. Acho que deve ter algum... Deve ter...
Eu acho que tá. O meu deu 3,6. Tá por 10 a diferença.
I have not made the calculation now, but this is what we are working with these solutions in the thesis of Nick Klammers. And I remember this value at the end, from 20 to lower, 20 milligram per liter to lower of TOC. I have not made the calculation of now, but it has, in my mind, I have this value of 20 or less, 20 milligram per liter of carbon from methanol of less.
Aí uma outra dúvida que eu fiquei, né, ao utilizar o metanol, né, poderia ser utilizado um outro solvente orgânico para preparar essa solução estoque? Por que essa minha pergunta, né? Se nós estamos adicionando metanol, mesmo que em baixo quantidade aí, ele vai estar mais ou menos, então, aí parecido com a concentração dos seus contaminantes orgânicos, né? E sendo o metanol um sequestrador de radicais hidroxila, isso aí não estaria afetando o seu processo?
Elizângela, you can answer. He's asking things that we have here developed before you come. So you need my help, I can tell you, okay?
Okay.
Really? Okay.
I think I'm gonna need the help. I believe that the methanol was a, how can I say, solvent. I'm not a chemist to say, but I think it's more, it has a higher solubility of more compounds to a one solvent. I think it's a broader solvent to many compounds, and you add less organic carbon to the solution because of the molecule of I don't know if this is correct, in comparison to other solvents, the polarity or not.
Por exemplo, e no caso da acetonitrila, ela poderia ser utilizada?
I think
Elizângela, I can answer because this is a methodology that we developed before you come.
Okay, so you can answer Sixto because I'm just guessing.
Alan is asking about matters that for us were we make a lot of questions before using methanol. So yes, of course, we can use acetonitril, but by any reason, methanol is able to dissolve better the emerging contaminants. This is the main reason. Between the different solvents that we have to use, we use a solvent that was not very volatile, a solvent that was not very expensive, not very toxic, so we have avoided to use acetone and so on. I remember we checked the same acetonitril and methanol. I am talking 10 years ago about that, is this type of things. And later we choose methanol because of, after checking solubility, because remember that the intention was to have a very high concentration of emerging contaminants for provoking that when you spike, you introduce a very low quantity of methanol. This was the objective. In this condition, we checked different solvents and methanol was the better from this point of view. And you are right. This is a OH scavenger, but all the times we have been playing with simulated water that could be difficult to treat to be very similar to real wastewater. So assuming that methanol is a OH scavenger, we want to have something inside the water that could be similar to effluent where you can find a lot of OH scavengers. So this, in the background of the work that Elizângela has done, this was this previous experience of our group trying to work with a lot of emerging contaminants at the same time in a simulated effluent that has groundwater that is difficult, plus an organic that is also difficult. So this, at the end, provoke that the results are more realistic before you go to application in real wastewater. This is the general philosophy in the back of the experiment that Elizângela has done. And I have to say that when she came, perhaps we do not explain her the reasons of everything, but in the back there are reasons for all these matters.
Okay.
Imagine. And also, Sixto, I was thinking because and also Alan, because of the results in the real wastewater without the fortification, we did the efficient. It was very efficient and compatible with the without fortifying the effluent used in the methanol. So I don't know.
Yes, remember, Elizângela, that we began with this in more or less long time ago, and our intention was always to provoke a simulated water that will be difficult to treat, to be able to work in difficult conditions. This was more or less. This is because of it, for example, we have had methanol, because we want a small concentration of organic, similar to effluent. Alan is totally right that these things are sometimes surprising, but in this case, we try to simulate real conditions and to work with a lot of contaminants, a lot of emerging contaminants. Without the methanol, Alan was impossible to work with a lot of them at the same time. This is the main reason.
Ok, thanks. Na página 120, na figura 4.2, né, nem você fez todo o trabalho, né, com a matriz ali natural de água ou do efluente da estação de tratamento de esgoto. Aí, nessa figura 4.2, esses experimentos foram feitos em água destilada, né? Isso.
Oh, yes. I had some in the beginning. Sorry.
Assim, não seria mais coerente ter feito na mesma matriz que foram feitos os experimentos?
Yes. Actually, our idea with in the beginning of the experiment was to work with an easy metric so I could start the experiments and also start to perform and do all the analysis, and also we could see the highest efficiency of degradation without the interference of these of the components of the metric. So what was the baseline of degradation of compounds in distilled water, and also yes, it was in the beginning more or less this. So this was the highest degradation of these compounds just for photolysis and for photoperoxidation is like this, and it would be lower in real wastewater because of the light attenuation and all the inhibiting effects of the metric.
Ok. Daí, então lá na página 126 e 127, né, nas figuras 4.5 e 4.7, né, onde são comparados os resultados, né, para diferentes concentrações de ferro na 4.5, na presença e na ausência da superfície refletora de alumínio, né, essa é 4.5.
Ok.
A diferença ali, né, mais notória, foi para a concentração, para a menor concentração, 0,18, né, 0,018.
Yes.
Esses experimentos, pelo que eu estou vendo ali, tem a barra de erro, né? A barra de erro dentro ou não?
Yes, it is very small, yes.
Que nem ali, por exemplo, essa diferença foi mais notória para menor concentração, né?
Yes.
Depois, na figura 4.7, né? A gente vê também ali, né? Você tem o gráfico para a somatória dos compostos e outro só para a cafeína, que foi o seu composto mais recalcitrante.
Yes.
Né? O que você tem ali é uma melhora, né, na velocidade inicial de degradação, só que ao final a eficiência foi a mesma, né?
Yes, in the end, the efficiency it's the same. It's over 80% in this case with the lower concentration of the contaminant.
Daí, na página seguinte, na 128, né? O que me chamou a atenção, é que nem ali eu acho que deve ter um erro, né, na figura A, não é 0,054, acho que é 0,1, né, na ausência de alumínio.
Yes, I'm sorry, I detected this for the presentation. So in the figure 2.5.08, the letter A, it's in the full symbol, it's 0.1 millimolar of iron. I'm sorry, I added the accumulated irradiation and I don't know, I did some mistake here.
Mas aí o símbolo fechado realmente é sem o alumínio, né?
É sem o alumínio.
E 0,1 e o outro é 0,054, mas com alumínio, né?
Yes. I think I did again the same.
Assim, por exemplo, também fica difícil ali para comparar. Se fosse a mesma concentração, na ausência do alumínio, a degradação está sendo maior, né? se fosse 0,054, mas é difícil comparar porque são concentrações diferentes, né?
Yes, the idea when we did this experiment in the raceway was to see if with the aluminum, we could use a lower iron concentration and achieve a high efficiency as we achieved with the 0.1 without the aluminum. So for the lowest concentration of contaminants, 20 milligrams per liter, we could see that for the lower concentration of contaminants. For the highest concentration of contaminants, we thought that there is not enough for the degradation.
Então, por exemplo, então você está querendo comparar o 0,54 com 0,1 para falar que com 0,54 você tem a mesma eficiência que 0,1.
Sim.
Mas não seria o caso, então, de ter feito mais dois experimentos, um com 0,054 na ausência de alumínio e outro com 0,1 na presença de alumínio?
Then the aluminum would be the 0.1 with aluminum, as we did with the raceway. We did that with the real wastewater in the next section. We did this with the real wastewater, and we saw that always 0.1 is better. It's a catalyst, you have more catalyst, the better. And we did this with the later on with the real effluent, with the real contaminant. We had to select experiments too.
Por que eu estou fazendo essa pergunta? Se você olhar na figura 4.5, o 0,54, né, não houve diferença na ausência e na presença da superfície refletora, né? Então, aqui, né, e assim, né, eu achei que talvez aqui, né, não sei, no meu um ponto de vista pessoal, né, talvez, né, fosse aí, né, pertinente, né, ter feito aqui o 0,54, você já até tem, né, ele aqui na ausência do alumínio, ele dá igual, né, e para comparar, não sei, né.
Yes. And later we did that with the real wastewater, just to confirm this.
But Alan, in the figure 4.5, there is a slight difference between when you have aluminum and when we didn't have. But if we are compare the concentrations of iron, of course, I know what you mean, that there is no difference between when you are analyzing just the with aluminum and without, but when you are like a very, very low concentration of iron, we have a difference, but of course it's very, very slow. But when you have a 0.0554, we have like a slight increase of the efficiency. But as Elizângela said, this part was done in Spain, but we did it with not natural, but tap water, and then Elizângela did again with real wastewater because the things change.
Assim, o que eu vejo ali para menor concentração de ferro, tem sim, né, essa melhora expressiva, mas aqui foi testado em maiores concentrações, né, para maiores concentrações, a superfície refletora, assim, não tem uma melhora tão expressiva, né? Então, foi nesse contexto aí que né, a minha dúvida, né?
Yes, in fact, it
was
a small difference, Alan. That was why there was a bit increase in the 4.5 in.
Porque até se você for lá na página 136, né, na figura 4.11, né, fica mais notório isso, né, que realmente não tem uma diferença aí na ausência e na presença da superfície refletora para 0,54 e 0,1. Os resultados são iguais ali.
Very similar, yes. Just the difference in the beginning of the reaction. I think in each part we had to select, like with Sixto, we tried to have a strategy to explain each thing, with different sets of experiments. And I think that was the idea for the raceway in this first paper, right? This first set of experiments natural in the tap water, to see if we could use this strategy, even though it was it is a small difference at first in the figure 5.4, 4.5. We still wanted to apply this, thinking of what happened in a larger scale, because this was in the lab reactor, if the difference would be the same.
Porque aí, né, você fala que os resultados de 0,54 foram próximos ao de 0,1, não é isso?
Yes. Also the other reason, I'm sorry, Alan, it's because I forgot to say, in this case, the reaction that we used also the 0.0545, even though the difference is more than the 1 milligram per liter, the black one, it's because of the initial degradation rate, it's the best one. So we saw that we could not reduce so much the iron concentration, because then the reaction is less efficient. We had this, you understand?
Ok. Porque, ó,
Yes.
Mas aí, então era basicamente isso que eu tinha, tá, para perguntar, Elizângela. Assim, os apontamentos aí, as dúvidas, né, não são no sentido de desqualificar nada do trabalho, tanto que o seu trabalho aqui tem todo o mérito, já está publicado, né, em excelentes revistas. O contexto mesmo aí das perguntas, né, foi algumas dúvidas, né, para reflexão. Eu agradeço, né, fico feliz aí pelas respostas, né, mais uma vez, parabéns, né, pela forma como você respondeu, né, na arguição, pelo excelente trabalho. Desejo para você aí todo sucesso, né, com pós-doc, e espero que logo você também aí, né, esteja aí na área. Infelizmente, hoje o cenário, temos poucos concursos, mas acredito que em breve você possa também estar estabilizada, né? Então, parabéns, agradeço você, a professora Camila, ao Sixto pelo convite, pela confiança, tá aí, até uma próxima.
Thank you. Muito obrigada.
Thank you, Professor Alan, for your contributions. We think that this is good for the students to have those kind of discussions, and I know Elizângela knows about that because she works so hard, but it's very important to have this kind of discussions and questions. I would like to say thank you again for you, and then I wanted to invite Professor Sergio to have his contributions in this work. It's a pleasure for us again. Thank you to accept our invite, and please feel free to have your questions and discussions.
Okay, Camila. And Elizângela, thank you very much for the invitation. Good morning, everyone. Still good morning. Good afternoon, or probably in Europe, in Spain. I'd like to say hi again to Sixto. It's a nice to meet you, to meet Carla, and also Alan. It's the first time we are in a public defense together. Alan, myself, Carla, and I participated during the qualifying section of Elizângela's thesis. So I think many things that I would like to say that have already been said by the previous examiners. I would like to start saying that this is a very nice piece of work that Elizângela did. It's a very relevant research topic. You studied an AOP, a simplified AOP, trying to use solar energy to thinking about scaling up this technology. And I think this is a very good thing that Grupoa, led by Camila, tries to do. They always think about the fundamentals of AOP processes, but they are always thinking of scaling up their technologies, and they are always concerned about costs as well, and also in doing a very nice work concerning about the analytical procedure. So I think Camila and Sixto supervised you very well. Camila, I consider her a very prominent researcher in AOPs in Brazil. So I think you were very well guided, and it's no surprise that you come here with a very nice piece of work. There's no doubt that we are facing here a PhD thesis, and we are arguing a PhD candidate that for sure will be a very bright future. Elizângela, I'll try to make some broad comments regarding your work, and I'll try to take no more than 30 minutes, okay? So okay. If I'm too long, you Camila can just say that I'm nearly to finish my participation here, okay?
Okay,
first
no
of all,
worries.
Elizângela,
feel free to have your contribution. No worries about that.
I think the thesis is well written. The experiments, as I said, were very nicely devised and executed. The data, it seems to me that it's been carefully treated and thoroughly discussed. So I think that there is a few comments on the document, on the written document. I'll hand it to you later on by email so that you can spot some minor points that could be improved, okay?
Okay, thank you so much.
I would like to start in the justification section. Okay. You said many things there I liked. I mean, it's clear to me the importance of your research. I think you should discuss a little bit more why you selected these chosen contaminants of emerging concern. Why you picked those 6 compounds. In some parts of the document, you said about the properties, because I understood that you chose them because they have different properties and all of them could be analyzed in one single analytical methodology. But I think you should also try to add some justification regarding the environmental toxicity or the environmental legislation, which might be different from comparing Brazil to Europe and to other parts of the world, right? In some ways, you try to justify the antibiotics, trimethoprim and sulfamethoxazole, consider them potential agents that can boost or develop the antimicrobial resistance in bacteria, right? But for the others, it's not clear for me that they are the most harmful to the environment. For instance, acetaminophen, carbamazepine, caffeine. We find caffeine in coffee and tea. And so what is the environmental concern of caffeine? What is the environmental concern of paracetamol, of acetaminophen? So I think you should try to strengthen this point in this part of the thesis, okay?
Okay, can I ask something, Sergio?
Sure.
You think I should add this also in the justification, not only when I present them, but also in the justification, some very quickly, but short, something short, but in the justification.
Yeah, exactly. You can do this later in the document as you did, but at the justification, you should say to the reader why you picked those 6 contaminants from a very long list. I mean, you show that you can monitor hundreds of these MPs in wastewater, in water. So why you chose them?
I agree, Sergio. I agree with you, but Professor Sixto wants to say something. Just let.
Yes, yes. Only because Elizângela worked with this type of compounds, like in other situations. This is a recommendation we made for her. The reasons. I would like to explain you the reason, because perhaps Elizângela is not able to write this type of reason that you state in the thesis, because the reason is totally different to environmental concern. I will try to explain you briefly. The main reason of that is that we want to work with conventional SPLC with a mix of different emerging contaminants for avoiding the use of LCMS in routine. So we try to find a mix of contaminants that are easy to separate in a chromatographic column and to measure by SPLC. This is one reason. The second one is that they are stable and do not suffer photolysis to be confident from the point of view of the experiment. So in any moment, we take care of the environmental concern. Why? Because the quantity of emerging contaminant you can find is in the range of several hundreds in every water. So to focus one or another because of environmental concern, we decide that this was not for us enough reason for that. And secondly, the initial toxicity. Caffeine, we know is in coffee, but when we are removing contaminants from the effluents, it's because we don't know what is going to happen with them in the environment. So caffeine could be converted but to other compounds. So I would like only to point out that the Elizângela using a complicated mix of emerging contaminants, easy to analyze by SPLC, and that are stable in water. This is the main reason, to obtain a lot of information that later could be applied to municipal wastewater treatment plant to remove a mix of hundreds. This is the main intention. So we were not focusing them because they were especially important, only that they were easy to experiment, with them. So this is a very practical reason, but it's only to point out that perhaps Elizângela, when we recommend her to work with them, she was not aware about these reasons. Okay.
Okay, I got it. But I think you should be, Elizângela should be very clear of this and make it clear at that point.
I think I totally agree that she should write in the thesis. Yes, because these are reasons.
I'm afraid of people reading her thesis and think, okay, this should be the contaminant that we must prioritize, or
no.
These are the ones we should concern most in regarding wastewater treatment.
Yes, I will advise Elizângela to write a paragraph to explain very well why we have chosen these compounds. Okay.
Yeah. Okay. Sorry to interrupt, but I have to agree with Sergio. Yes, I totally agree, and I partially agree with Sixto, but I think that it's correct when he said that it's for to allow the quantification and other things. That it's very, very important when we choose the compounds. But when Elizângela was in Brazil before to go to Spanish, Elizângela did a very, very how can I say, a high investigation about the occurrence of the contaminants in the Brazilian waters, and about the papers that was published. And then because Sixto work with DESA so many times, and for Sixto this is usual, like these are microcontaminants, and these are like Of course, they have environmental concerns, of course, because Sixto knows about that for a long time ago. But for us, we are worried about what kind of contaminants we have in Spain that we have the same in Brazil. We have this kind of...
Yes, I'm talking of the work in Almeria. Yes, sorry, only about the work in Almeria.
We are looking for the same contaminants that there was occurrence in Brazil and in Spain. So I think that Sergio it's correct when he's worried about that. But this is my fault because I asked to Elizângela cut some parts of the justification because sometimes I think that the text is too long and too boring. And no, Elizângela, just cut that. And now I think that you are right. We have to put again the parts, then Elizângela, just one paragraph, then Elizângela just justify that this is important emergent contaminants that have been found in natural waters in Brazil and in Spain as well, something like that. I agree.
Okay, I think a good way around this would be try to justify saying that you work with different contaminants that belong to different classes that have different physical chemical properties, and you wanted to see the behavior of these different classes in the photoreactor, right? Without caring too much about the environmental concern. But I think you should also add some comments on this. We need to prioritize them. I mean, there's a long list of contaminants. Which are the ones that we should concern? In my opinion, we should concern about the ones that pose a higher chemical risk. We need to do a risk assessment. Which are the compounds at which concentration that they cause an environmental impact to the aquatic organisms or even to human beings? So I think you should add something, some comments on this in your thesis. Okay, Elizângela?
Okay, I will add. Also, just one comment for diclofenac and carbamazepine, they are also used in the Swiss legislation for the... So they are among those 12 contaminants. So I think for them, for sure, I can add more of this justification. And for caffeine, just one comment. I don't remember the paper, but I think there are some recent studies about the toxicity. I was surprised as well. But I think the concentration is quite higher. But also caffeine is being detected in a high elevated concentration also in the effluent. I can discuss a bit.
Yeah, I anticipate a discussion I would make about caffeine. I noticed that you try to somehow focus on caffeine. At least you brought the reader attention to caffeine many times in many graphs. And sometimes you refer to it as a process indicator because it's recalcitrant. And if you monitor caffeine, you could thereby use it as a surrogate. In other words, I mean, I can follow caffeine behavior and then indirectly say that the photoreactor didn't perform well or did. So in my opinion, I mean, I think you should focus on those that are that have the most environmental threat. So I don't agree too much with this approach. But anyway, I wrote down in many parts of the document. It's up to you to discuss this with your supervisors. Okay. We tried ourselves here to see whether caffeine would be a good process indicator. And we see that sometimes using chemometrics, that caffeine goes to one side and the other contaminant to the other. I mean, caffeine doesn't mirror the behavior of hydrophobic compounds like the estrogens, and it cannot use it in this way you mentioned here many times. So it's something that you could discuss with Sixto and also Camila. Okay.
Thank you. Professor, if you could send us, or I don't know, add the information of your work with this, I can also discuss it a bit.
Okay.
I don't know. Okay, thank you.
Okay, moving forward on chapter 1, I like it very much. You did a very good systematic literature review, and I don't have many comments to make on that. Just a quick comment. On page 32, you present equation 1.3 when you show that iron 3 can be reduced back to iron 2 using radiation, right?
Okay.
H&E, you presented that. I'm not into AOPs as you are, guys. This is something I would like to know. What is the minimum wavelength needed to perform this reaction, the reduction of iron 3 to iron 2?
The minimum, I think.
Yeah, because you present H, Planck constant,
okay.
times Ni, which is the frequency. In other words, I could translate this as wavelength. What's the minimum wavelength we need to input there?
Actually, I think I would say the opposite, the maximum wavelength, because sometimes UVC works very well, but you don't necessarily need to go to the vacuum UVC that is too low, because it's a lot of energy. You don't need even, you can apply just the photolysis. You don't need the reagents. You can have some disinfection with this low wavelength of UVC. But we are worried more with the maximum light, because we try to go to the visible light, to the sunlight, to work with this reaction. So for the photo-Fenton, we could, I don't know, Camila can correct me, about 500 and something for the solar photo-Fenton. Okay.
Okay.
So the maximum is more important to go to sun.
Yeah, when I say minimum, because the higher the wavelength, the less the energy. So I mean, what is the minimum energy you should input so that iron can be reduced? My question is it sustainable to do this reduction under solar radiation? Is that the reason you need to add a chelating and complexing agent?
No, the reason for the chelating agent is to make it soluble in a higher pH. So we can have this for example, this iron aqueous ferrous substance that in the photocatalytic cycle will react with the light and liberate the ferrous iron. It is soluble only in a low pH. So
yeah, but listen, my point is, if you put a UVC light, I assume that all iron 3 would be reduced to iron 2, and then you wouldn't have problem of iron precipitation in the system. Is that the reason that under solar radiation, the process is not that sustainable, and then to avoid iron precipitation, you need to add a chelating agent?
No, not necessarily. And also there is another question with the use of artificial UVC. Also we have some worry with the toxicity of the reaction and the cost of the light. We try to use to not have lamps and the irradiation system. I don't know to say. How can I say, for a future application in the industrial scale that Sixto said, we need to, there are some strategies that have been under investigation. Should we perform just a continuous Fenton, dark Fenton during the night? Or should we use the less or more environmental friendly LED lamps? There are many possibilities, but the idea, okay.
Elizângela, just interrupting you just a minute. Sergio wants to know what the role of the sun, the wavelength of the sun, and the cycling of the iron. And you know about that. I know you know. And about what is the, how can I say, the advantage to use solar wavelength, the wavelength that the solar has, and then the artificial lamps. When you use like a monochromatic lamp that just emits 254, or when you have the solar spectrum. Is that no, Sergio?
Yeah, I mean, because I don't know this into depth, okay? And my question is, if I used the UV light, would it be necessary to use a complexing agent? That's put in simple words.
Yeah, if you want to work in a neutral pH, you need to. Because because of this, this I'm pointing to my computer. The equation 1.3 because of the iron HO2, the ferrous iron aqua species.
Okay.
Because and with the chelating agent, this is soluble in a. It's because of this,
because iron 2 solubility is higher than iron 3, right? So that's why I reckon that if you use the UV, you could have more iron 2 species and then work around neutral pH without problems. Okay, but you clarified this point.
It's the things here that we have to have in mind here. It's about the wavelength. When you have just like 254, it's not like the iron will not absorb this light. The iron absorb from Sixto could interrupt me if you want. 450, 455, and then when we have 254, we will have more reactions from the broken off the hydrogen peroxide because the hydrogen peroxide absorb more this wavelength than the iron species. So in this case, we have to put like the complexant to allow the solubility of the iron. And then, of course, when you have not monochromatic lamps, and we have the lamps that emit in another spectrum, in another wavelength, we can have the cycling together, because the light, when the iron absorbs the light, the cycling could be increasing. So
one second. It's only because I think we are like in a circle. I have the feeling that Sergio is asking about why not provoking the reduction of iron with 254 light. Because if we provoke the reduction from iron 3 to iron 2, the iron 2 is more soluble, and we are going to be happy. This is the main question. This is because I was trying, because
as written in equation 1.3.
Yes, mainly because we are talking about photo-Fenton. So in the moment that you apply, you have iron 2, immediately hydrogen peroxide oxidized to iron 3. So iron 2 is almost never in water.
No.
It's always iron 3. Because the reduction to iron 2 is slow. It doesn't matter if with UV light or with solar energy. The oxidation is very quick, the reduction is very low, very small, very slow. So what we needed, mainly the complex, is to keep the iron in solution at neutral pH. But I have to say that to work in 254 or to work with solar light, it's always economical discussion. But from the point of view of the kinetics, is that you have never iron 2. You cannot measure iron 2.
Okay.
Because of the presence of hydrogen peroxide.
Okay, so Sixto, answer my question. The problem is not to keep iron soluble as iron 2, because iron 2 is always consumed very quickly. So I think you should add this at this point in chapter 1, when you discuss the importance near this equation 1.3, the importance of having the addition of this complexing agent, okay? And also, if you could, also include that discussion that Alan raised about costs, about the cost of chelants and different chelants that could be used, etc. Okay?
Okay, I could also add the pH solubility graph we have for the iron. This will be clear.
Exactly, yeah.
And I'm sorry, I think in the equation 2 is iron 3 with a hydroxyl, so it's not iron 2. I'm sorry, I was making up things.
Okay, so moving on to chapter 2, I like it very much. I mean, this chapter supported 2 papers. So what else can I say? There isn't much to comment on that, really. I read somewhere on page 108 that you adopted 30 watts per square meter for total UVA. Why this value was chosen? Does it represent average radiation in Spain or in Brazil? Is there a reason for that?
Yes, that is the reason. This is an average value for solar irradiation at noon, not only in Spain, but in Brazil at noon, direct irradiation at noon of the sun. So it's a good condition of irradiation that is close to real conditions. But of course,
Okay.
this value vary in winter in the locality, but it's an average value. I can get this value
I mean,
to a reference to cite this.
As a matter of chance, I had a radiometer with me yesterday here in my place. And then I was outside and just measured. It was a bit higher. It was 12 milliwatts per square centimeter, which roughly 120 watts per square meter. So I think that in some places in Brazil, it might be higher than that.
No, but Sergio, we also need to see the wavelength range for this UV. In this case, we use it from 300 to 280 to 400. It's like part of UVA and UVB. And if yours is like total visible light, the sunlight, it can be higher. In our equipment, for example, for 30 watts per square meter of UVA, it's like 268 here in Brazil of the total.
Okay. Yeah. Good. And another question is on page 123, you discussed very well that the treatment capacity depends on the micropollutants concentration. And you discussed about the different results you had with different concentrations. And you used the 20 micrograms per liter of each contaminant. My question is, do you think that this represents the concentration of these peaked contaminants in Brazilian sewage? 20 micrograms per liter.
Of which and the total being
well, you mentioned, I understood that it was each MP, right?
So it's in total like 120 with the 61 of them.
Yeah.
So it's a bit higher, but it's closer to some. I have found some. I have tried to some in different papers from different works. I don't know. I think I put it in the target micropollutant section. Oh no.
Yeah, I think.
Yes, in page 108, and I did not add a paper from Brazil, but I can try to find one because I had to look, Sergio, for papers that could give me all the concentrations of all the compounds they investigated and to sum these. And sometimes they had this information only in the supplementary material. So I tried to find some of these papers to reference this information. And it can vary a lot. I could find from a few micrograms up to more than 100 in some papers. I found paper from Greece, from the United States.
I think you could focus on Brazil, and there are plenty of works carried out even in UFMG. A rented project, Camila knows about it. Vasali, MSc dissertation. And there are also some studies from Paraná, from São Paulo. I mean, you could quote them. And normally the values are lower. It couldn't go further than 200 nanograms per liter in case of sulfamethoxazole, diclofenac, trimethoprim. And this agrees well with the results that was found in Almeria. You present them later on. in your document.
Yes.
Okay.
Sergio,
Okay.
we know, we know about the very amount of the work that there is results published in Brazil. As I know, I told Elizângela did a very long revision about this occurrence of the contaminants in Brazil and the papers that have been published. And of course, Vassalli, I think that Master of Vassalli was about hormones, if I remember, Maria Clara knows more than I. And we did the same with Vassalli, with Lydia. I don't know if Lydia was in a thesis. Yes, the problem is when you collect, there is sometimes.
I think Lydia was surface water, no?
No,
natural water.
Secondary effluents from conventional sludge, activated sludge. Of course, we have small concentrations, but you know more than I that is difficult to do in low concentrations when you want to see the degradation because the limit of the detections and the equipment that you use. So in chapter 2, Elise did in Spanish. Of course, they have more infrastructures and more knowledge about the chromatography analysis, and they have the quadrupole. I don't know if there's a name in English, but over here we don't have access. We just have access with the HPLC DAD, and we have to dope it to spike it, the effluents in a little bit more concentrations because these allow to identify the degradations. But we know that sometimes could be less than there is an occurrence in natural waters. This is like a common comments of the referees when we publish papers, but I think that everyone knows nowadays that this is necessary to allow the quantifications in the chromatography analysis. Sixto wants to say.
Yes, but I mean, I think the main objective was to think about treating effluent from secondary, and not natural water, but effluent from a secondary treatment. And the concentration of around 100 micrograms per liter of a summatory of all the emerging contaminant is very close to reality. In the effluent from a secondary.
But 20 micrograms per liter seems too much for each one of them. At least for the six. Yes, at least for the 6 of them, compared to Brazilian reality.
Yeah, totally true. This is a summatory. We tried to provoke a summatory of 120 with only 6 compounds to be able to work with conventional HPLC. But we were thinking in the summatory of all, not the 20 microgram per liter, of course, is higher for each of them. This is true, totally true.
Okay, no problem. Moving on, let's go to page 127. You showed that at the best scenario with aluminum reflexive surfaces, the MPs were completely removed by around 10 minutes. And if we consider this time of contact, we see that there is no reduction of iron concentration as per figures 4.3 and also 4.8. In other words, it means that the EDDS has not been degraded at that time, right? My point here is, do you want, thinking about seeing the whole picture, right? Do you think that it's ideal to have EDDS in solution, or do you want it to be degraded because it has different and opposite effects, right? In some ways, it can obviously be reused, and Alan was saying about the costs of this complexing agent. So 2 questions in one. The first thing, can you think of recovering it from the treated effluent, assuming that it's not degraded at this point? Can you think of using ion exchange to recover and reuse it? And if it cannot be recovered, don't you think it would be better to have it degraded so that it would cause less COD and total carbon, in other words, less oxygen demand?
Okay, let me try to, I think that as Sixto has mentioned, the addition of the oxygen demand of the total dissolved carbon, it's very small. For example, for the effluent around 10 milligrams, it adds just about of 20 milligrams. It's very low. It's still very low from the point of view of discharge and for many reuse applications. And in this case, I have applied, Sergio, an excess of EDDS to make sure that, because I was thinking to have, I did not optimize every hydrogen peroxide concentration, EDDS. I wanted to these parameters to be in chemistry when you want the excess, so they do not are in absence, how to say, they are in limiting reagents. You know, I did not want it to limit the reaction, but the ideal application is not to waste this EDDS, is to work with a small concentration of the chelating. You optimize this. So some works now, people have been working to a smaller ratio of iron EDDS 1:1 and not 1:2. I wanted in this case to not limit the reaction, but I believe we need to work with we need to optimize this to not waste the reagent. And regarding the recovery, I don't know if this would be viable with the information I have read so far, but I don't know if there is something published about this, because I don't know if some ion exchange.
Okay, but even using a limited amount, you would add at least around 20 milligrams per liter, right? In a 1:1 stoichiometry. 20 milligrams per liter of EDDS would cause around 18 milligrams per liter of COD. I mean, it might be low, but it might compromise the discharge limits. I mean, it depends on the
I'm sorry, no, it's like 20 milligrams of carbon, of dissolved carbon, not the EDDS. So it's more, it's not a lot of carbon. I should have added this information of the DOC value.
Yeah, but I did some math here, and I found that considering the relationship 1:2,
in the beginning,
you would add from 50 to 75 milligrams per liter of EDDS. And the relationship is roughly 1 gram per liter of EDDS causes 0.95 grams per liter of COD. So it's roughly 1:1, okay? If you consider the minimum formula of EDDS. But anyway, I think you should at least say this, that the target is to use the least amount of EDDS, and that would cause, at the worst scenario, the most COD would be, as you said, around 20 milligrams per liter. Okay,
I'll bet this.
And finally, moving to chapter 3, I have just one question regarding this chapter, because I think I talked too much already. I think you should mention the benefits of the proposed disinfection in comparison to the usual practice in many words. For instance, in the United States of America, they use chlorination, and we know the impact, the adverse effects of chlorinating treated effluents. And I think you missed that. You could say that at this point on page 176, saying that the proposed solar disinfection is much better than the chlorination because of the obvious reasons, and that wouldn't promote the formation of chlorinated compounds.
Okay.
And also on page 177, I think you could also mention that the solar peroxidation, you showed that it performed well for disinfection,
Yeah.
but it removed, I think at the most 14 or 15% of
14.
micropollutants, right?
Yes.
I think you should stress at this point that it depends on a risk assessment, whether it suffices or not. Maybe if I do a microbial risk assessment and also a chemical risk assessment, I can come up to the conclusion that the problem is the microbial risk, not the chemical risk.
Okay.
So I could easily use solar peroxidation for disinfection. It would be much better than using chlorination. So I think you should add some value to these results, complementing this discussion, saying that not always I have to use the process as you did. You adding iron, adding the chelating process, chelating agents, chelating compounds. Maybe the solar peroxidation is enough, because in some conditions I may need just to remove the microbial contaminants, not the chemical ones. And that depends on the legislation, that depends on the reuse of effluent, that depends on the risk assessment that you should, I think, mention at this point, okay?
Okay, I will.
So to conclude, yeah?
No, just saying I'm gonna look for and add some this discussion.
So to conclude, I knew at the qualifying exam that you were a bright student, you were very well supervised, and you wouldn't be any problems to come to this point with a very good work. And I would like to stress, to highlight the importance of this exchange program, the internationalization of our graduate program. You went to Almeria. The Almeria Solar platform is well recognized for its excellence in research. So you did a very good job, because obviously you were very well supervised and you were committed to the work. So congratulations, and I wish you success in your future. Thank you very much, Camila, and Sixto for the invitation, and the word with you again.
Okay, thank you, Sergio. Thank you again for your contributions. As I was expected, it's very, very important for us as well. And finally, we want to invite Professor Thiago to do his contributions with the work. Professor Thiago, thank you again to accept our invitation, and please feel free to do his contribution.
Thank you for the invitation. I'll try to talk at least a good English, but my English it's not that very good. So I'm probably going to talk English, Spanglish, Portuguese.
Don't worry, it's not bad than I, so we'll be fine.
So it's a great pleasure and a great opportunity to learn with your work and to learn with our colleagues here. It's a great pleasure to meet Sixto. Thank you. So the other colleagues said everything. Your work is well established. You have 3 good papers in 3 good specialized magazines, and with great impact on the area. So I'm going to talk about some special things about the methodology, and some curiosities. So I'm going to start with your thesis title. So your chapter 1, you identified that the term contaminants of emerging concern are not well used anymore, right? It's not used anymore. So why don't you change to micropollutants or just contaminants, emerging contaminants? Because your bibliometric analysis showed that the number of papers that are containing these terms changed. right? And then change it in two kinds of perspective, in my view. The first one, it's because I think that the papers now are doing discrimination about what is its pollution and what is contamination. That's the first question I want you to answer. If you think it's because of that, the changing about the terms, and second, why do you think it's important to distinguish the synonyms that you point out on your methodology?
Okay.
It's clear. I'm going to say in Portuguese.
It's clear. No, okay. Oh no, I think you want to know about if I should change my title and the focus of the work because of my biometric analysis.
But I'm going to say in Portuguese, just to be clear.
Okay.
I don't think in English was good. Se você poderia mudar o seu título, né, de contaminantes de preocupação emergente, né, para micropolutante.
Professor Thiago, don't worry, we understand you. That's fine, okay? Your questions was very clear and your English is good. Don't worry about that. I think that Elizângela could answer because we did this kind of discussion, not discussions, but argument about the title, about these words in the title. And so Elizângela, if you
just
could.
Curiosity, okay? It's just curiosity, but don't you think that your work showed a great result about this bibliographic, I don't know, bibliografia?
Yeah.
Bibliography. It's difficult to say in English. And you point out that there's a difference because on the years about the terminologies. So what do you think this is happening and why? And why? Could you say?
But
in a personal and a practical way. It's
in a practical way. I think the term of the contaminants of emerging concern have changed a lot during the years, even for the definition, until some definition was established. So this was changing a lot. I've seen also about this term micropollutants, that it's a very general term. So you can have a organic micropollutant, you can have an inorganic micropollutant, and I think this is the reason why we see more of micropollutants. It's a broader term. But at the same time, I think it might not represent exactly. Sometimes I can get, for example, in the bibliometric analysis, I can grab some papers that were not with the focus of, for example, the contaminants of emerging concern with this lower concentration of contaminants of organic that can have some effect. And this we could see this in the result that I have over 400 papers in the table 1.4.1, the updated portfolio before reducing this this number of papers. And the idea in this analysis, Professor Thiago, we want to have like for 100, maximum 100 of papers to read all abstracts and titles, and to have a final 40 or 30 something papers. And in this, I had a problem to reduce the number of papers and to find the answer I wanted, that was disinfection and the removal of the contaminants. So I think it's good that the broader, the micropollutant, but I think it sometimes is not so specific. I don't know if I'm clear for this, for the bibliometric analysis.
I think you are, but the figure 1.4.2, and you see like the last 5 years, you actually have increase in the terminology of emerging contaminants.
Yeah,
and I was thinking it probably it's because of Stockholm list of POPs.
Okay.
Pollutants of organic persistence, and I think that the researchers are careful about to discriminate these classes. I don't know. That's the curiosity why they are changing. So The next
I don't know.
Do you think there are sign-on in the end of your research of the chapter? Do you think micropollutants and contaminants of emerging concern or emerging contaminants are really sign-ons?
I don't know. I can be sure.
It just emphasizes the discussion because we have a broad list of compounds, right? So it was just curiosity, but
yes,
it was a good exercise to see what you did in chapter 1. Okay, let's proceed to your resume, your resume, your abstract. I think the version that I got, I think there's a kind of a problem there. In the last part of your abstract, you're like abruptly passed to your results of the second chapter and I think the third chapter without giving any extra to your resume. So yeah. I'm gonna read in Portuguese just after
a conclusion.
After esse trabalho apresentou, né? Não, sorry. Resultados demonstram, blá, blá, blá. Aí you go. Em seguida, uma superfície de alumínio aplicada no fundo, etc. So there's a abruptly cut in there. So you're explaining very good your abstract in Portuguese, and then you go to a conclusion of your chapter 2. So I think you should revise your resume and also your abstract because they are kind of there's this problem. I don't know if everyone's versions were like this, but I think that my version of the resume it's
the same. Okay, sorry, it's the same version. It's just one version, and this is just the writing. I sure will try to enhance this and make it a better abstract. And I think I could add the results from each chapter closer to the methodology or when I discuss to make it like in the thesis.
I think that your resume it starts like com o objetivo de reduzir custos. That's your resume starts there. All behind you're saying things that it's good, but it's on your bibliographic revision or your introduction and stuff like that. You can be more direct at this point. So this work we did bibliographic revision using bibliometrics, etc. Then you go to the chapter 2, chapter 3, and everything. But because you adopted an article style thesis, that's the reason why. Because an article style thesis, you point out your conclusions for every section. So sometimes you have this confusion, in my opinion. But I had this impression on your resume. So it's just that. Another curiosity is why you point out that carbon unactivated adsorption is an advanced technology. I'm not in the area of AOPs, but advanced technology for me, it's the application of something or basically chemical process, physical chemical process that degrade specific compounds or generally compounds. But activated car-qual is just adsorption, right? And when it's adsorption, you don't have, sometimes you have chemical transformation, depends on chemical of the layers, but
okay.
It's really an advanced process, activated car-qual. It was a curiosity.
No, I think sometimes, I don't know, sometimes I wanted to say advanced technology, not advanced oxidation technologies, advanced technologies in general with the membrane separation, which were advanced to promote a removal, not necessarily degradation of contaminants, and advanced to go beyond the removal efficiency in the biological process. I'm gonna check again if in any point I left this, if this can cause any confusion, but it's not an advanced oxidation process. And
yeah, it seems like that it was.
It's a physical chemical treatment. Yeah, I should not use this term, maybe.
So like the colleagues, I did some balloons with my commentaries. It was good that your presentation you changed it the drink water legislation. Huh? We have this on this month the changes.
Oh yes,
yeah.
Yes. I'm sorry.
So you know, okay, it's normal.
I did not update in the thesis.
Yeah, you already did in your presentation. That was a good thing.
Yeah.
So in your introduction, there's I think that, for example, in all your thesis, you have problems with scientific notation and algorithm, significative figures or significative algorithms. For example, in your introduction, in page 19, you put like 1,287 MWWTP with a common. So in scientific notation, but we have those kind of things in United States English, but I suggest that you use scientific notation. So until 1,000, the numbers are all together. After 1,000, you have a space
between the numbers.
You do not use common, but the scientific notation, I think that would be the more appropriated. But you have this all in your paper, all your work, things like that. Okay. Okay, so we're going to the chapter 1. Let's see. Okay, we talked about of equation 1 to 1.1, 1.2, equations 1.3.
From the photo-Fenton.
Yeah, so this is in EPH3, right? I think that what Sergio meant before was like, I think that the solar spectrum in the UV region, it's like less than 10% of all the radiation. And probably it wouldn't be more efficient. I think that there was the question about being more sustainable or something like that. In the chemistry point of view, I would like to, we understand that is in aqueous solution, but we should good to put on brackets that is on aqueous solution.
Okay.
Right.
Okay. In bracket. Ah, yes. Aqui.
Yeah. And it was good to see that you put the first hydroxide complex of iron. In this pH, it's probably the more abundant compound. So I think it's okay. So why in your bibliometric analysis, in the after everything, you just chose 5 papers? It's something related to the methodology that you use,
yes.
Or 5 is there a number that you guys choose?
No, Thiago, it's from the ProNoC, the systemic analysis of the ProNoC methodology, and also the idea is to, if I can read all the papers, but to a in-depth analysis and to say, this is a strong point of this paper, this is not so strong, this is a possibility to work in the area, this paper have all the information, so we need to choose to do this in-depth analysis with just 5. But it's not like we decided 5. I took this number 5 from the methodology.
Okay. In page 48, another curiosity, you say this, another group of 6 manuscripts which showed really relevant titles and abstract were added to the portfolio as an exception, since they were published very recently and therefore had only a few citations. And then in the end, you shows another 3 papers from those I'm sorry, and these exceptions papers, 3 of them were in your finalist. So don't you think that it's a personal choice and something that should be statistical all the way? So do you think your bibliometric in the end, you already published that? So I was really curious because in the end, you already chose 3 papers. They are good papers, but you chose them because of the systematic criteria that you use. But it is a personal choice. Do you agree with that or not?
A bit, but it also reflects in the main question that guided the literature review. Are there any papers that present the simultaneous information on disinfection and the removal of the contaminants? So what I had to do, it was like I had a lot of papers, over 400 papers with information disinfection or removal of contaminants, but few of them presented the simultaneous results that I wanted to see. They show for the same monitoring of the process of even lab scale or large scale. I wanted to see these simultaneous results, and in the end, just few papers had this. And another thing that I could see is that more recently, in recent years, these papers are taking this into consideration. So it's a bit of a personal choice, but it's because of the papers. The papers with best information on the simultaneous that I wanted to see in the paper were the recent published ones. So this is my interference on the methodology prognosis, but this is not just, there is another paper from the group that published this methodology. They also use this adjustment of the methodology to add the recent published, because they are good papers. They give this information, but because they are recently, they could not achieve a high number of citations to be used. So yes, it's not a perfect methodology. I think there is not a perfect methodology for everything, but you can have some structure in the keywords and everything in the search, but in the end, it's the literature review. You have to get a bit personal, I think.
Yeah, because in the end, more like 3 or 5, right? 3 or 5 papers you chose.
Yes, because
so,
of this.
Yeah. But
yes.
they are good papers, but it was curiosity, because I think the best thing you show in chapter 1 is all the insights that you have with the things you proposed to research. Oh, it's a good thing.
Can I just say something also? If I had to do this analysis again, including 2019 and 2020 papers, I would find more papers with this both information, even from everyone here in the defense. So it's very complicated because it's limited to the time of the analysis. The papers every day we are publishing, and this is changing constantly.
Okay. On page 56 is another curiosity. Small doses of oxidants were sufficient, 0.1 millimolar for disinfection purpose, while higher oxidant doses were necessary up to 0.5 millimolar for the removal. I'm not in the of course I'm not of the area, but a 5 times concentration, it's already considered a high dose. Just for curiosity, just 5 times we enter into a class of high doses.
No, it's not a high dose. It's just in the comparison here. I wanted to say
that was higher, just it.
That was higher in comparison to, in this paper, in comparison to what they used for disinfection, but just for this paper, not everywhere.
Okay. So let's go to chapter 2. I'll finish. Chapter 2, in page 86, is the same from the first, the reaction. Okay.
Okay.
I kind of interested here. You put the a complex reaction here, ligand to metal. So you put trivalent iron plus L, right? And
Okay.
you have the wavelength, and then you have the complex, and then the complex produce iron 2 plus L. Do you agree that you should put that's a general expression, because this will change with pH, will change with the kind of complex agent and everything. So kind of pass me the impression. So I ask it here that it's normal to, it's common sense to put this way.
No, I think it's a very simplified way of showing the ligand.
Okay.
To explain, I could try to go a little bit in depth, perhaps with the EDDS example, for this here.
Okay, there's a lot of questions that the other colleagues already did. So let's go to page 95. 95. So here there's a lot of questions that I did here. So the main one is how many experiments you did on your analytical curve, because you don't explain how you calculated the LOD 5. So you must you must put there were 5 curves that you did, and how you calculate it. You calculated by the standard deviation of the angular coefficient of blanks, or the incremental deviation, and etc. So when we look at what you called A and B, I believe there are the coefficients of your curve, right?
Right.
And it was for 50 microliters, and in the figure 2.3.8 for 100 microliters. That's correct?
That's correct.
Okay.
I see, Thiago. It's incorrect in the graph because I changed the X and the Y. I changed them.
That's what I
you know, and
because the angular coefficient, it's totally different and should not be the difference. You just change the injection, right? So
not the injection. When I did the equation in the during the calculation, I inverted both of them. So it should be the inverse.
But you did inverted regression.
Yes.
But inverted regression, we have problems with that, right? Because the dependent variable now, it's your X, right? When you do an inverted, sometimes there's no problem, but in chromatography, you should never do inverted regression, linear regression. You understand what I'm saying?
No.
I'm going to say in Portuguese.
Okay.
Really slow. Na figura, na tabela 2.3, né? Você tem o A e o B, que eu acredito que o A é o seu coeficiente angular, certo? Né? Para 50 microlitros, né? E aí embaixo você tem lá as curvas, que tá difícil de identificar de quem que é, né? E aí é para 100 microlitros. Eu acredito que você só aumentou o volume de injeção, então as características do método são a mesma. Então o coeficiente angular deveria ser dentro do desvio padrão, né? Das 5 curvas, igual, né? Aí você falou que você fez a inversão, né? A inversão você só fez matematicamente, assim...
Isso, matematicamente no Excel.
Você calculou a curva fazendo o método inverso, usando o X como variável...
Peraí,
usando as variáveis dependentes e independentes, ou seja, agora a sua variável independente é outra. Você fez isso ou não?
Calma, peraí. É porque aqui são duas coisas. In this graph, we have the mean area by mass. We multiplied this concentration of 10 to 10, 25, 50, all of them by the volume. We injected both 50 and 100 micrograms per liter.
So it's the mass.
So this is mass.
In the mass on the column.
Yes.
Because so you should write that. That's mass on the column. So Because
Yes.
if just mass, we could imply that was the same kind of curve from the table 2.3.2.
Okay.
So so that's the mass injected on. So the mass injected.
Yes, and we try to show that we could.
This is strange because the mass injected, the last point shouldn't be 0.2 micrograms, I think. It should be different. Check this, but the coefficients, if you didn't do this, should be the same. We agree?
We agree.
If you just change the volume of ejection, you have an analytical curve, right? And if you have a signal response that it's in your instrumental requirements, let's say in your method. So when you do a 2 times injection, the angular coefficient should not change, it should be the same, because you are in a DAD equipment. It's a spectrum, you understand? So absorbance to concentration. So when you do a double injection, the concentration will double. The sign, the signal, not every time you're going to double, but you have from lambda here a correlation there. But the angular coefficient should be the same. So it shouldn't be different. You see, for example, the first curve, I believe that it's from the yellow one. Yeah, you have 412.95x and the linear coefficient. And on the table, when you see, you have 0.9 minus 0.12. So it's really different. So check this when you multiplied the mass, and what you did here, it shouldn't be like this. It's strange. Another thing that you should check is the linear coefficients that are negative. So you should check there is no systematic trend on your analytical curve. How you validate them? You check for you did an histogram analysis, an error variance to check there is no systematic trend. I ask you that because when you look to your LOD, for example, for acetaminophen, you pointed 6 micrograms per liter. And the first concentration that you injected, it's 10. So when you do the ratio 10 to 6, and you see your angular coefficient, the signal, the factor of response, it doesn't quite justify the value. So it would be good to put how you calculated your ALD based on what. So like other colleagues said, put a chromatogram on your appendix or supplementary material should be a good thing.
Okay, I will add the calculating sheet that I used.
Put the number of curves that you did. It's important. And the coefficients, they have units. So the angular coefficient would be in the first case that you said we're going to be area for it's going to be area for concentration, and the second will be mass for area. So they have units. So put the units on that. Okay. And I think part of your word you mentioned that R2 is the linear coefficient. It's the determination coefficient. They are different in the kind of a Pearson statistical analysis. So check that too.
Okay, this is determination.
And trimethoprim had a 1 determination correlation. Didn't think that is kind of strange? So there are things that you should
have to change again the injections and the Excel.
You should check that. In all your work, but it's a personal opinion, you put, for example, things that I think that are not experimental. For example, in this section, you explain what is high pressure, high performance liquid chromatograph. You explain that. So it shouldn't be here. This is experimental section. So it's what you did. You don't have to explain anything about the technique itself. Should be in the introduction if you want, or just point a single line and you put some reference. You shouldn't explain anything here. What is high performance liquid chromatograph? Is an experimental section. So you have to do what you did, how you did. So in the results sections, you're going to explain why. So the figure 2.3.8 and table 2.3.2, then I'm going to ask you, I think that you're doing it in an engineering perspective, because you're saying that those results are just supporting you. They are not results of matter of the whole work, because these are results and should be in the results section, not in the experimental section. These are results. Are results. So if you don't want to put them in the results section, you should put them in supplementary material, and the experimental section should be what you just did, because those are results, and results should be in the results section. You agree with that?
I agree. I think it gets a little bit mixed up, because we are for engineering, and we try to show that I've tried to understand what I'm doing. I'm not just injecting something and not thinking about it. But I agree that it's not the standard organization of the methodology. So I don't know. I tried to discuss with Camila how we can arrange this to put in the supplementary to organize this better.
They are results, so I think that you should put in supplementary material and make your experimental section more clean. And then there's some confusion, in my opinion, about the 150 compounds. In your thesis, you say that you're going to work with 6, but then in the middle you present all these results without explaining I don't know how to say in an explicit way. I got a little confused about the 150 results, and I was thinking that it was the paper of Sixto that I looked it up. They did a work, I believe, with this number of compounds, and you use it in your thesis. I don't know. I got a little confused with this.
Okay, so the methodology they have there, they investigate up to 150 compounds in 2 analyses in this paper for, I don't know if but I think the methodology is exactly from the campus manhãs. But when I analyzed my effluent from these 150, we detected only 60 of them. So these are the ones that are shown in the results section. So from 150 that we look at, we could only find 60.
Okay, I almost finished. Use natural water. I think that Sixto said was subterranean water.
Yes.
Yeah. So okay. So you should specify what's natural water in your work.
Okay, for sure. I will try.
And another thing that I got confused when you say what's real secondary effluent, because for your solar and Fenton experiments, you do a filtration step, right? Using sand filters and stuff like that. After the filtration, do you think that it's the right way to say that it's a real secondary effluent?
I think so, because this is a kind of, for example, for the application of the photocatalytic reactions, we know that the penetration of light is very important to reduce the light attenuation. So it's necessary to have any kind of filtration of large particles to perform a photocatalytic reaction.
But it's not real anymore.
It's real. I got it from and also when we use this, we had one paper recently with Camila. I don't know, Sixto also can correct me, I don't know, the professors, because they wanted to say in English actual effluent and not real effluent, because everything is real from the perspective that everything is real. it's not hypothetical,
Yeah.
and that actual effluent, because we want to separate the simulated, on which we go there, each solid reagent, we produce the simulated effluent, from this one that we get from the municipal wastewater treatment plant. So we are not adding things to the, of course, I'm fortifying with the contaminants later on, but the inorganic, the organic compounds, everything is from the actual municipal wastewater treatment plant.
Yeah, the matrix was real. Yes, it's not like a simulated matrix. It was a real matrix. It's a common.
Yes, I mean, the meaning is that you spike on the real effluent, you spike the compounds, but the effluent was real.
Yeah, because the next section you say, because on the method from the tandem mass spectrometry, you say blank, sample, and standards. But in the method, blank and sample are basically the same thing. You agree with that? Because you're injecting every day the filtrate or the effluent. But that's your blank because you're doing what we call an addition standard curve, right? Every time. So your blank is your sample. And you say that real, I got really confused with this, but it's okay. It's just a matter of terminology. In table 2.3.5, when you put ND, not detected, it's lower than the limit of quantification, just because it doesn't, yeah, you don't know if it's not there. Probably it's not there, but you don't know that. So you have to put that it's lower than the limit of quantification, okay?
Okay.
Yeah, and check the significant algorithms on all the tables. For example, in tables in the table 2.346, for example, look the sulfate concentration. In the secondary influence, it's 103.49, and then you have 0.78. So what's the precision of this analysis? It's 2 or 3 significant algorithms, right? So make a standard of everything. Because
in this case, you are totally true. I always insist in the students not to use the results of the calculation, but to take into not the result of the machine, to take into the consideration the detection limit, to use the decimals. Yes, this is an error. So I think you understand me, no? I mean, it's really, the concentration comes from a mathematical calculation without taking into consideration the limit of detection of the method.
Yeah, the limit of detection and the standard deviation.
In this case, right? So sulfate should be 131 or 130, but not with so many decimals. This is true.
Yeah. So throughout your work, you have a lot of this kind of way of you put your results. So check that. When you did your lab scale experiment with artificial light, page 108, section 2.333, yeah.
Okay.
It was with controlled temperature?
No, that was not controlled temperature, but we monitored the temperature throughout the experiment, and it does not have much variation. I can add some information. I have the results also for pH and temperature.
And the volume, and you have the final volume difference? You have a lot of evaporation or not in the system?
Variation in the volume? No. We calculate, we did the work in such large cylindrical vessels to allow us to get not more than 10% of the volume of the reaction. So we have this calculated. Oh, I can get 5-10 points of 10-20 milliliters. I know how much I'm taking, so that I don't take more than 10% of the total volume.
Okay. In the figure 2.3.15, of diagram of total light and solar reflection for the
Okay.
reflexive element surface. 10, 40, 55 in the center are temperatures. I got a little confused here. It's temperatures or not?
No, no, this is the diagram of the reflection of total light reflection. From considering this AM 1.5, it's like a standard solar spectrum that that is used usually in this kind of work with solar light to have a standard of the solar emitted sun, and it's a half of the atmosphere. 1.5, it's like the proportion of atmosphere, so it's a standard for the solar spectrum in the world. So they try to check the total reflection instead in different degrees, the black 10 degrees, red 40 degrees, in the degrees
of what?
Of the incidence
The incident light. Okay.
Yes, the incident light, and they check the reflection for all the spectrum.
But do you think that I got a little confused here? We cannot discriminate what's the diagram of total light and the diagram of solar reflection, right? Can we discriminate on the figure?
No, on the figure, no.
Okay,
this is just a from the how can I say the
so you have to check this.
The company.
Yeah, I think it's just total reflectance. Okay.
In the name of the figure. Okay.
The graph is just total reflection, but what? I think that was the total light.
Total solar light.
The graph is for the total light. Total
light.
solar light. Yeah.
Total light.
To check this.
I will change the name solar light.
Yeah. And then on your experiment with the RPR, you said that the mixing time was determined experimentally with a silane pulse test by monitoring the concentration of ions every 2 minutes for a total of 30 minutes. So when you look at the table, 2 minutes is everything mixed.
Yeah.
So there's no need of this table on the manuscript, on your thesis, because you didn't do before 2 minutes. You did the test before 2 minutes, like 30 seconds, 10 seconds. I know you grab a sample, you did something like this, or you started with 0, 2 minutes.
Yes, 0, 2 minutes,
yeah.
And then it was the shorter.
There's no need for this table. You should just point out, and we believe you. So why why 30 minutes? It's not enough time. Why 30 minutes? I didn't understand why it's 30 minutes.
Because we didn't proceed into 2 hours. Because if with 2 minutes, it's already the concentration.
So why we investigated 30 minutes? I didn't understand why.
You want, I can answer him, because I think. Do you mind if I can answer this question?
Yes, you can, because I don't remember correctly.
Yes, and it's only because I think I can follow the main intention. This table is not necessary. You are true. If enough, if you write from 2 minutes to 8 minutes, because nothing happened later. What Elizângela is showing here, that this was an experiment of 30 minutes, because at the beginning we didn't know if the mix was going to be so quick.
Yeah.
So really the experiment was 30 minutes, but really interesting results were all in the first 4-6 minutes, okay? Because the intention was to check that the mixing time was, how quick was the mixing time, and it really was so quick. So I hope I have answered the question. So it was an experiment of 30 minutes, and these are the results during the 30 minutes. But Elizângela should state only the first 2 or 3 points. It's not necessary to write more.
Okay. I just have 3 more questions and we finish. Okay, Camila? I was really curious about the proportion of iron and the EDDS, because the question is, it's like 1-to-1 reaction, right? On the pH that you use it to test it, but the thing is, I would like you to point out how you could differentiate, make the difference between what you called it's soluble iron or dissolved iron to the total iron on your experiments. The question is because on the results section of figure 2.4.1, the B chart, you say dissolved iron, right?
Yes, it's the filtered.
Dissolved iron is what you call in the sum of the iron complex with EDS plus iron that is free in solution, like in 3-valent form, 2-valent form, or it's just filtered?
It's just filtered.
But so, there's any difference in an aqueous solution of filtered and not filtered? There's a huge difference?
There is a huge difference because when we can see the precipitation of the going from particulate iron to precipitate, and we see in during the reaction the reduction of the total.
But it's still dissolved. But it's still dissolved. If you don't do iron hydroxide complexes and everything is soluble, everything is dissolved there. So I got really confused about the notation of dissolved iron, because the iron complex, iron EDDS is soluble, right? It's solved. So when you stop the reaction or the peroxide attacks the EDDS, so you don't have the iron protected, right? So he starts to form iron hydroxides, right? And if it's pH of 7 to 8,
they would precipitate. So this, I don't have the result in this graph for total iron to compare with the dissolved one. But over in chapter 3 on page 172, I have one from experiments of the chapter 3 that I present in black, the total iron, and in red, the dissolved iron. And you can see this phenomenon of the precipitation and reduction of the dissolved iron during the end of reaction.
I saw that chart, but you didn't do any statistics, so they are like the same, right? It's a graph that...
No, I don't have enough. Yes, I don't have enough to make the statistics. So, but this behavior, Thiago, I can show you. I didn't put this in the papers because we had a lot of figures, but this happens when we see the decomposition of the complex. Later on, you have the reduction of the iron concentration, and the total iron is constant in the rest of the reaction. This in the experiment from Spain. Here in Brazil, I noticed this is a small reduction in the end of the reaction here.
And but I have to do more things. You should point out the number of experiments. All your charts and graphics, you don't put the number of experiments you did. For example, it seems like you did just one time.
Okay,
I think that you did a lot of times, because many times we start with things got not working, right? And then we
and then repeat and repeat. And in fact, for these experiments with the contaminants of emerging concern, the error is very small in terms of duplicates, of replicates. But for example, for the biological and also the other disinfection experiments, we need more biological replicates. It's very important.
To finish.
Okay.
And to finish. When you start your thesis, you say that the problem with conventional treatments is that they use the word removal, but they are not removing anything, right? Because you have a phase transference, right? They are partitioning to the particulate, to the solid phase, and everything. But when you do your experiments, you use the word removal. So don't you think that you're going against what you said, that the justification of using AUP? Because if you don't analyze byproducts, you cannot say that you have 100% mineralization or degradation. So removal, like other colleagues said, sometimes could be not the way you apply that, because you're saying, I have a removal almost like 80%, but you really remove the compound acetaminophen, but acetaminophen could be transformed in something else in the reaction, right? In your system. So
Yeah,
you not really remove it.
I put degradation,
but we
remove efficiency, I think.
We did remove a 60% of acetaminophen, but we are not speaking about the byproducts. I think that I agree with you that when you use just removal, but when you put like the efficiency of the removal of the contaminants, we are, I think, right. I don't know if another professor thinks about that, because if you are thinking about removal of the compounds, you are removing the compounds. I know that could be or could have byproducts, but at this case we are investigating the removal of the contaminants. So for that, or for those contaminants, we remove 60%, 14%. And I think that when you put the efficiency, that this means that we didn't remove, we are not indicating mineralization. We are indicating that we removed 30%, 14%.
No. I totally agree with that. I just questioning the use of the word removal, because the justification of using AOP was because the conventional process actually don't remove the compounds. They make a phase transference. But when you analyze the effluents of the system, you say that it had a removal. So
okay, I can change to degradation
I just point out the use of the word removal.
Yeah, but I don't agree with the things that the conventional process don't remove. I think that the conventional process remove a small part, but the most part is absorbed on the solid phase. But there is oxidation and removal of a lot of kind of contaminants.
It's just a curiosity, just to open a discussion about the use of removal, the word removal. But yeah, it's a kind of, it's a kind of.
We can phase, you can, Sergio is saying here, the phase transference is also a type of removal, but from liquid phase. Yes, we know, I agree with you. But okay, we can just looking for the phrases and the.
But if you're in the solid phase and you discharge that on a sanitary.
Yeah, we are transferred, but
you're transferring the problem. So it's not a removal in a global way. I just joking, guys.
Okay, it's not 100% of removal. It's not 100% of removal.
The word removal.
Okay.
Yeah, we will take care about that.
No, it's just because like the justification of the conventional process. I just implied to the. Yes, just because of that.
I read the same phrase in the conventional process that Elizângela put it, but I think that this context is not right. We have to change this context, because conventional process could remove, but not in the total. And there is like a small part of oxidation, but there is more than like transfer for the solid phase. I know.
And to finish about the removal of bacteria. There is an application of chlorine dioxide. It doesn't generate byproducts, and I think that it's called a clean chlorine. So if you think it's interesting, you should check about the application of chlorine dioxide in some plants for disinfection. To compare to AOP, following what Sergio said about chlorination. And thank you. Sorry if I was inconvenient. I think that's
no worries about that. No worries. And this is the
congratulations. Congratulations, Elizângela. It was a nice and good work.
Thank you.
And thank you, Camila, Sixto, and all the other colleagues.
Thank you so much, Thiago. We will looking for these contributions, and I think that will be very good to have you with us. I like so much about this thesis defense because we have over here a very, very good kinds of researches. I would like to say thank you again to spend your time with us in this morning. And then I would like to say some words before Sixto for Elizângela. I think that Elizângela did everything that she could. Elizângela is like, I don't know, because we have some audience over here in YouTube, so I can't say like that she is like the first, the five best students that I had, because we have like a predominance of women in our group, and they are like, do you know, like jealous, and this could be like fight for me. It's not true. It's not true. But Elizângela, it's very, very kind person. Very, how can I say, Elizângela, take care about each things that she's thinking. I never had to worry with Elizângela in a lot of things. You know, we have our job. In our job, we have to take care about the students and to take care about the things of the labs and to take care about the methodologies. And with Elizângela, it's too easy because Elizângela allowed that we could supervise her the best way that I could, because Elizângela makes everything easy for me. And she could understand and she could to have some discussions like with high quality. And when she didn't know, she go there and research and investigate and come back with the answers and with questions as well. And I am very glad to stay here today. Unfortunately, we could do it like in the normal mood. We have to do it like online mood because if we were like in UFMG, we could eating some like how can I say, honey
bread? I don't know.
Elizângela could bake some honey bread, very delicious. And then I know you, Elizângela, since I think that 2011 maybe, and then we did like a junior research with me and master, and then we come back because you trying to work like on the private institutions, and I just rescue and Elizângela again, stay with me, don't go. And Elizângela now, I think that she is ready to develop her own like researches, and I hope that we continues our partnership for a long time. You will be always it will be very pleasure to have you in our research group, and you are part of our research group, of course. And thank you so much for everything that you did for us, for the group, for me, and is it. Congratulations for the best person that you are.
Oh, thank you. I'm going to try to not cry, sorry.
Yeah.
But thank you so much for all the opportunities. And I don't know what to say, just thank you so much for all the opportunities. I know it's a long way working and trying to do our best, and sometimes laboratory is kind of, we plan something and you have to like, I plan the 3 times the time to do something because I know laboratory every time it's a surprise and everything. And thank you so much. And I hope so. I don't know how the future is gonna go, the opportunities in these years next to be, but I hope to continue with the postdoc and see every opportunity. And thank you so much.
Yes. Sixto, if you want to say something.
Yeah, but I mean, not so much because you have stayed, all you have stayed, I have realized with Elizângela when she was here is really consistent and very confident. So this is, her work was always very easy to follow, because she was really very consistent. This is very important. She always was looking at the results and taking care that everything was logical. And everything was, so from my point of view, Elizângela is a person that later, when she will continue supervising other people and when she will continue in this type of work, will do a good work, because he's very, how to say, self-critic. This is very important. So from my point of view, this is totally true. This is one of the best PhD students I have with my hands in the last year, and mainly because of it, because he's confident and self-critic with the work.
Yeah.
But she should learn that being in this way, at the end, in a 200-page documents, other people is able to find errors and to find things that could be better. This means that we can never be alone working. It's better to be with different people, collaborating and so on, to reduce the number of errors, because if you collaborate, the main advantage of collaboration is that you reduce the number of errors. And that's all. I mean, I was very happy with this collaboration. Elizângela was in Almeria six months, if I am not wrong, between November of 18 and May 19. And she did a very nice work, tried to clarify if aluminium was or not a good idea. Because I always tell the people that we are developing methodology, not giving solutions, because the solutions are later when you have a real case with your methodology, you can arrive at the solution. What we have now on the table are different possibilities: aluminium, not aluminium, EDS, not EDS, more iron, less iron. It's only to know what happened when you change these parameters looking for a specific solution. And this PhD was in this way. This was a set of different possibilities of managing photo-Fenton, how to evaluate, and later when we have a specific wastewater, we can adapt everything to this specific wastewater. So thank you very much in any case. It was a very, very nice collaboration. Elizângela was in the middle of this collaboration, but I'm very happy also collaborating with Camila and everybody from Brazil, because I mean, I have collaborated and they continue with collaborate with Carla. I collaborated in the past with Alam. So this is a small family.
It's like it's our. I think that everyone is like your pupils, no? Because Carla stay with you and Alan as well. So it's like a family.
Yeah.
Okay. Sixto said one time, and we never forgot. I and my research group, when we published our first paper together, it was Chemical Engineer Journal, and it was like a challenge, of course, because Chemical Engineer Journal is always a challenge. It's I think that's 12 impact factor. And then when everything was fine and we published it, Sixto sent like a message. Thank you, Elise. Congratulations. You are the core of this work. And the core is the most important part of our body, I think. The core and the brain, of course. But without the core, we couldn't do nothing. So, and with the breath, of course. So, Elizângela is that you are the core of our research group, Elizângela. And I know about that because I do, and I did a lot of Pilates. So without the core, we are nothing.
Thank you, Camila. Thank you, Sixto.
It's just a joke. So, Elizângela, now I have to say to waiting just a bit